So as you can see, I'm wearing my T-shirt that Carol Artico, my respiratory therapist, gave me. And do I have to come closer to the camera like this or back? Anyway, it says awesome. It has a llama followed by a tree. So this is the entry quiz to the seminar this morning. It's like our secret handshake. Okay, well, I guess it's 9 o'clock, so let me get going. I'm going to put this into speaker mode. Put you over here. We'll see you a little bit later, Zoli, or sooner during the discussion.
Okay, I just wanted to hear Ramon's voice.
Okay, so welcome back, everybody. We will begin the morning session, day 2 of the 7th annual Montreal Oscillometry Summer Seminar, coming to you from McGill University in Montreal. Again, a shout out, thank you to the team that made it possible and our corporate sponsors who were kind enough to provide us the funding to have an enjoyable networking supper and also our lunches and coffees. To remind you that it is being recorded, hope, and the recording will be available with the other archived recordings on the Respiratory Effectiveness Group website over in the UK. So thank you, REG, again. We have relocated from the Research Institute of the MUHC to McGill University campus. And we were, oops, that's too fast. We had a wonderful networking supper last night at Thompson House, and we have photographic proof that everybody had a good time. So those of you, please note the networking supper is not available in the hybrid format. You must come to Montreal. So speak to those who are here and they will encourage you to come, I'm sure. So welcome back to the seminar. We had a great program yesterday. We have another fabulous half day today. And I'm going to hand the podium over to Sandeep Salvi, who's coming to us from India, followed by Disha Gorpale, who will also be speaking from Sunday's institution in Pune, India. So Sandeep, I'll give you the screen and welcome to the seminar.
Thank you, Ron, for those kind words of welcome and introduction. Both me and Disha, who is going to be the next speaker, we feel very, very sad that we couldn't make it to this summer, the summer program live because of the visa issues. But nonetheless, hope to see each of you all sometime sooner than later. I bring to you greetings from India, and I thought I would share with you some of the amazing experiences that we have had in setting up a training program on oscillometry. So I'm going to share that story with you from India. I come from India, which is a country that probably has the highest burden of chronic respiratory diseases in the world. There are an estimated 100 million people who suffer with chronic lung diseases, primarily including COPD, asthma, interstitial lung disease, and others. One of the key challenges that we face in India is the ability to make the correct diagnosis because of want of use of objective diagnostic tools. So there's a lot of underdiagnosis, wrong diagnosis, and this gets translated into wrong treatment and undertreatment that further worsens the burden from chronic lung diseases. I trained as a pulmonologist in India, did my PhD in the UK, and then came back to India in 2002. And one of the first things that I set up when I came to India was this training program called Spirometry Simplified. And this was with the realization that spirometry is not taught well in medical schools. Doctors are not aware about it. It's not that they cannot afford to buy the equipment, but just that they don't know what spirometry is, how to perform, and how to interpret. So we took it up as a mission to train pulmonologists and physicians from across the country by organizing this Spirometry Simplified program. We started it in 2005, and I feel proud to say that we have easily trained more than 20,000 doctors and technicians, all one-to-one with hands-on training. Now, when we started this program in 2005, we thought that we had made the best training module for spirometry, but little did we realize sooner than later that you still need to work a lot on it to simplify it so that doctors can understand it in a much better way. So from 2005 until 2010, it took us 5 years to simplify the training module for spirometry. And I can tell you that at every point of time, we thought that we had developed the best training module, the easiest and the most simplified training module. And then we changed it all over again because we thought we could still simplify it further. So 5 years of hard work, innovation, creativity, and collaboration, we developed this Spirometry Simplified program. Now, the impact that it had was quite massive. When we started in 2005, the sales of spirometers in India every year was a mere 50 spirometers. So, I mean, for a very large country like India, that was really, really peanuts. But then, with the advent of the training program, the number of the sales of spirometries went up, and today, I believe that at least 2,000 spirometers are sold every year in India. And I would like to take part of that credit at least to the training programs that we organized in India. And soon we realized that training of doctors and other personnel is absolutely crucial for the uptake of diagnostic tools in clinical practice. It's not the cost of the spirometer. It's not the other challenges associated with spirometry. It's just that the lack of knowledge that many doctors have. I got introduced to impulse oscillometry when I was in the UK just before I came back to India. And that was in the year 2000 at the University of Southampton when this good looking device was brought into the department as a research tool. It looked wow. I was told that it uses sound waves to measure lung function and that it was a very simpler tool and more sensitive to pick up obstructive airway disease than spirometry. I was fascinated by the looks of it and the thought that, wow, it uses sound waves to diagnose lung function. So when I came back to India in 2002 and set up the Chest Research Foundation, that was one of the first instruments that I bought for research purposes. I bought it, but I did not have adequate knowledge to use it, and there was no training available at all. I then looked around for if anybody else knows how to use the machine. There were about 5 impulse oscillometries available in India, across India, but none of them who were using it knew how to use, who had it knew how to use it because of lack of knowledge. Now, having seen the success of the spirometry simplified program, we thought, why don't we develop a simplified program for oscillometry? And we started working on that. And we asked the company, the Jaeger company, which is run by YSS at that time, to support training programs so that the uptake of the utilization of the devices would improve. I broke my head for 10 years with Jaeger, and I got the same answers every year. Our company does not have any policy to train doctors. We do not believe in investing money in training. And I tried very, very hard to gain some support from them so that we could disseminate the knowledge that is associated with oscillometry. But I failed with Jaeger. I then challenged myself to get my knowledge base sorted out of oscillometry because it's so difficult to understand oscillometry. So I took up this challenge. I wrote to the Breathe Journal and said, would you be interested in having a review article on lung oscillometry? And when they said yes, I said, okay, let me now start reading and I'll simplify it as much as I can. So I got this article published in the Breathe Journal in March 2015. Tried to simplify it as much as I could, but still a very long way to go. Then something happened in 2016, probably inspired by the article that I wrote in Breathe. Some of these engineers from India, located in Bangalore, which is in the southern part of India, they decided to develop an oscillometer. an FOT of monofrequency of just three frequencies, 5, 12, and 20. And they came to me and said, we want to develop an oscillometer, and we would like to partner with you so that we could help us with the clinical development of it. So I was associated with the development of the Antlia FOT device in from 2016 onwards. I was also part of the clinical development program for PulmoScan, which was also partly developed in India at around the same time. I had heard about the TremoFlow machine, but it came much later, and I did not have the opportunity to work with TremoFlow. But these three instruments suddenly came in 2016. The Chest Research Foundation, where I worked, unfortunately shut down, and then I started my own foundation called the Pure Foundation, the Pulmocare Research and Education Foundation. And one of the first things that I decided to do with this new foundation was to disseminate the knowledge about oscillometry to doctors. The first thing that I did was we set up a network of lung oscillometry research called ARISE, International Network for Lung Oscillometry Research. And then we gathered together a group of 27 pulmonologists from across the country who had an oscillometry device, 5 pediatricians, and there were 3 from international, from Malaysia and Sri Lanka and so on. And we started doing simple observational studies. And then soon we realized that we need to standardize oscillometry. We need to train the doctors in the network about oscillometry. So we started this new program called Omega, Oscillometry Training Program for Lung Diseases. And we were very fortunate to get the partnership of the company that developed the FOT and the partnership of a pharmaceutical company called Cipla. And together we initiated the Omega, or the Oscillometry Training Program for Lung Diseases in India. This is how the brochure looks like. It was me and my colleague, Disha Ghorpade, who's going to be the next speaker. We were the only 2 people who gave all the talks. It was a half a day. It is a half a day training program where we cover all the basics and how to perform and how to interpret and so on. So this is how we initiated the Omega program in India. So far, we have trained I believe, more than 1,000 doctors across the country. We took it up on us as a mission to sensitize and educate doctors about oscillometry and its clinical application. And so far, we have been quite successful. And the sort of response that we have been getting from the doctors across the country has been very, very rewarding. Some of the key challenges and the key questions that we encountered during the training programs are these questions. And I must tell you with all honesty, it took me a while to find answers for these. Are FOT and iOS similar or different? Even I was not very sure in the beginning whether they're the same devices or they're different devices. Which one is better? Why do you use frequencies between 5 to 20 or even up to 37 hertz? Why is reactance negative at low frequencies? Why does it become positive as the frequency increases? What is phase in phase and what is out phase? Very, very interesting questions, but I'm sure all of you all probably realize that they're not very easy to answer to lay people. What is inertance? Can you explain with simple examples? And are elastance and compliance the same? And I just thought I'll just share with you some of the innovation that we did to educate the medical community in a very simplified manner. So are FOT and iOS similar, or are they different? And if at all, which one is better? So then we developed this simple animation to show that we force oscillatory pressure waves of different frequencies into the respiratory tract during normal tidal breathing. We overlap these oscillatory pressure waves, and the output that we measure is very simple, just pressure and flow. The oscillating pressure waves can be generated by different mechanisms. Now, FOT is a very generic term for all devices. And I know doctors started calling iOS as the important device. So everything was called iOS. Even if it was not an iOS device, they called it as iOS. I had to explain to them that iOS is one type of an FOT device where impulses are sent in, like square waves. But there are other ways of doing it. We have the monofrequencies and then we have the pseudo-random noise. Clubbed together, all of them should be called as FOT. So even iOS is an FOT, is a type of FOT. That was a challenge to explain. But then why is iOS the name that comes out all the time? And then I had to explain that the photocopying machine was invented by Xerox. So because they were the ones who invented, the name got stuck to it, Xerox. Now the photocopying is done by so many different machines, like Canon and Fuji and so on. But when we get a photocopy from a Canon, we still say, I want a Xerox from this machine. Uh, so that's how the word iOS actually has become so powerful. And we need to replace that with something that is very generic. And I thought we should call this as lung oscillometry test, although I believe that the correct word terminology should be respiratory oscillometry test, but then the short form comes to be ROT, and that's not a very nice name. So I thought maybe we should promote NOT as the lung oscillometry test. Why do you use frequencies between 5 to 20 hertz and 37 hertz? Oh, this took me a long time. And it took me a long time to realize that when Arthur Dubois developed the device, one of the first things that he did was he identified the resonant frequency of the lung. And then I started understanding that every organ in the human body has its own resonant frequency. The lung has a resonant frequency of between 7 to 12 hertz. And therefore, if you want to study the capacitance and the inertance, which are on the either side of the resonant frequency, then you certainly have to include these frequencies, 7 to 15. And then for capacitance, you need to go to the left. And so 5 was the number that was decided. And to study the inertance, 20, but the resonant frequency kept on varying between, so the young children have very high resonant frequencies. So you need to expand from 20 to 30 and so on. Certain diseases like COPD, when they have severe obstruction, the resonant frequencies can increase up to 30 and 32 and 35. So that is the reason why we had to include these frequencies in the instrument. And then the discussion about why 5 hertz and why 20 hertz and how does it help. Then the simplification that the low frequencies travel longer distances right up to the bottom. The higher frequencies travel for shorter distances up to the large airways. And then the distance, the gap between the two actually tells you what is happening in the small airways. Now, to simplify this, we came up with this idea of how the AM radio uses very low frequency, and therefore it can travel for thousands of kilometers. Whereas the FM radio, which uses very high frequency sound waves, they travel only for very short distances for up to 50 kilometers. And that's the fundamental understanding of why low frequencies travel long distances and high frequencies travel short distances. Just like the ultrasound signal. If you want to go deep into the abdomen, you need low frequency signals. If you want to measure the thickness of the cornea, only few millimeters, then you use very high frequency sound waves. So I think that was very, very interesting to develop. Then why is reactance negative and how does it become positive? What is phase in and what is phase out? And so we tried animations with different sorts of things like this. So resonant frequency, both the flow and the pressure, they perfectly match with each other. In the when you have the lower frequencies, then the flow goes ahead of the pressure, and at high frequencies, the pressure goes ahead of the flow. And to even simplify this further, we thought of we showed these images of just to explain. So if you look at the one in the middle, elastance, where flow goes ahead of pressure, and because resistance is pressure divided by flow, because the pressure is lagging, it's behind the flow, it becomes a negative value. And opposite happens with inertance when pressure is ahead of flow, and therefore it becomes a positive value. So images like these, animations like these, helped us a lot in simplifying stuff. This was a real challenge. What is inertance, and how can you explain this in a simple language? So inertance is a bag of air that remains in the lung after your tidal breath sound. So below the tidal breathing, you have your functional residual capacity, which is around 3 to 3.5 liters of air. That bag of air has got some mass, which needs to be overcome for the air to reach the alveoli. And then I realized that the weight of 3 liters of air, which is the FRC, is around 3.7 grams, which is the weight of a pen drive. And to look at the opposites, 3 liters of helium weighs only 0.5 grams, and 3 liters of sulfur hexafluoride weighs 19.2 grams. And then we started showing videos of, if you inhale helium, what happens? And this is a video to show what happens when you inhale hexafluoride.
Sandeep, we have no sound.
We have to imagine.
We'll
That's
get
a
it off
very
the line.
low.
Love the hashtag. Send a private message.
I hope you got the voice as well.
No.
Just to,
I didn't.
oh, you didn't get the voice. I'm
No,
so
it's
sorry.
silent. But you can just.
But you can imagine that.
Yeah, yeah.
Just to show elastance and capacitance, we actually got these fit bands, and then we showed them how easy it is to stretch. It comes back to its original position, and how the thicker ones are very difficult to stretch. So low compliance, high elastance, high compliance, high elastance, high compliance, low elastance, and so on. So we were able to actually use some of these in our training programs. Who else is organizing educational programs on oscillometry? So I know there's a very beautiful ERS program on oscillometry with Professor Charles Irwin, Professor Jeff Maxon, and Professor Peter Calverley. It's a very, very good program, which I got to learn a lot. But then the others are being organized by the companies that make the oscillometries. So Jaeger has a program, then the Pulmoscan has one, Thoracis has one. I think we need to develop more of these training programs. So just to summarize, for oscillometry to gain popularity and uptake in clinical practice, it is vital to develop training programs that are simplified and scientific. And for that, we need passion, hard work, commitment, immense creativity, partnership with engineers to simplify what is reactance, what is resonant frequency, illustrators, animators, industry support, so that they can fund some of the training programs, oscillometry manufacturers, pharma companies like what we are doing now. And then obviously it requires good leadership. So this was what I wanted to present as an experience of how we are trying to make oscillometry an important diagnostic tool in India, and the challenges that we have tried to overcome through our training programs. I'll stop over here. If there are any questions, I would be happy to answer.
Thank you very much, Sandeep. And we are very sad that the Canadian Embassy wasn't able to issue you a visa to come. And congratulations on the training program. I think a lot of us could only dream of being able to train the number of physicians and technicians that you've done. So I appreciate the thoughts about the nomenclature. I had settled on respirator oscillometry, but I do take the point that it is rot. But perhaps, we're very fond of cannabis here, and we have representation from Colorado, so we could always think about calling it the pulmonary oscillometry. But I know that there are some questions, and so Jeff, I saw your hand up, and perhaps you can start.
Thank you, Charmaine. Thank you very much, Sandeep. That was an excellent overview of the efforts you're doing to spread oscillometry in India. Particularly effective, I think, is the training program that you established. It really sounds wonderful. We need more of that. I totally agree. raised my hand because I also want to dispel a myth that exists in the oscillometry community that the sound waves at low frequency travel further in the lung than the high frequency. That's was an analogy that Michael Goldman made long ago, somehow gathering how sound waves travel farther in Earth, like, and elephants can stamp their feet and communicate farther at low frequencies. But it doesn't actually work for the lung because the air is actually the same all the way through. And sound goes just as well for low frequencies, the frequencies we choose, to the alveolar region as the high frequencies. And if you think about it, the frequency dependence of resistance and even the reactance are very negative and very high. So the impedance to the flow, that's what impedance means. Impedance to flow is highest at the lowest frequencies. The lowest frequencies have difficulty because of the mechanics of the lung going through the lung, right? So it's actually the reverse, if I want to express it as plainly as possible. But it's more complicated than that. It's an impedance. All the pressure waves make it perfectly fine all the way through, but the flow is reduced more at the low frequencies because it's harder for them to actually, for the flow to be generated all the way through. So
No,
just want
wow.
to clarify that myth.
No, thank you so much.
Yeah.
Thank you so much. That's amazing learning for me as well.
Are there other comments? And Zoli, might you have some comments on?
Thank you, Chang Roy. Congratulations, Sandeep. It's an amazing effort what you have invested in this program, and I think the whole oscillatory community has to thank your efforts. What are you showing? Around
I'm showing Chung Wei how to close the chat. So carry on.
Okay. I fully agree with Jeff on his criticism that sometimes superficial analogies make more mass than help understand things. So we have to be very careful to make it popular and easy to understand, but not violate elementary physical laws.
Yeah.
It's very important. I'm very thankful to you to make this apparent distinction between FOT, well, it's called oscillometry for simplicity, or respiratory oscillometry. Now, not airway oscillometry probably, because it's not only about the airways, not lung oscillometry, because chest wall is included in the measurements, sometimes an equal partner in creating the opposing impedance components. So I would probably humbly underline the respiratory oscillometry term, and it's very good that you stated that iOS is just a subclass, not the very recent, a little bit archaistic or atavistic. From the old engineering approach comes back when you didn't have any composite signal to test mechanical systems or electrical systems. So it was a sort of fabrication of something. The sound waves, I don't like the term either, because we use, in terms of frequency range, infrasound, which is not audible. There are, of course, exceptions when you have a machine gun like the iOS. So the repetition of impulses 5 times a second, it is frictional harmonics, and not every patient likes this. So it is simply a pressure wave or a flow oscillation which we employ to evoke the mechanical response or the total respiratory system. Otherwise, so we can work and debate about for hours, but probably it is not the sense the sense is that oscillometry is taking more and more importance in the everyday lung function. And I think this is what the seventh summer seminar in Montreal speaks about. Thank you very much.
Thank you, Zoltan. That was absolutely brilliant. Thank you for those feedbacks and comments.
Thank you. And I've got Leonard and then Charlie. So Leonard.
Hi, Sandeep. Good to see you again.
Hi.
And thanks for your presentation. So, as people here in the audience know, I work with thoracists, and I've been to India a few times and done similar exercises as Sandeep has been doing. And the one thing I can sort of reflect on is that there's a difference between Europe, North America, and Australia and India. In that in India, almost all the sales go to clinical use. Very few go to research. Oh, we do sell for research as well, but the vast majority of devices, and I think that's the same for the devices you're involved with, they probably go to clinical use, which I think is a very stark contrast with the European, North American, Australian side, where they say, no, we probably need more research before we can employ this and really use it. In India, they're just using it. And yeah, that's sort of, I think it's sort of testimony to what your training or training in general actually will do, because these people are learn this from the start, ideally from med school. They will be aware of it and they will put it to use in their clinical practice. So I think kudos to you.
Thank you.
The only other jurisdiction I know that's doing anything similar would be Hajime in Japan. They've got an extremely high penetrance on what's essentially a closed market, because Hajime has a similar education program.
Yes.
And he has actually trained the physicians there, not even on pattern recognition, which is what I'm espousing, but rather on color coding his outputs to correspond with the inhaled medications that are used in India.
Yeah.
Which is a really brilliant thing. He bypasses the whole concept of any physical principle and makes it very, very practical.
I mean, part of this is, of course, the big need that Dr. Salvi started with, you know, with the huge prevalence of chronic respiratory diseases in India. So, of course, there's unmet need. But I think this is a good way of meeting that need.
And I think maybe it really sort of underscores the importance of actually education. It's important to get the, you know, to get devices out in terms of clinical use, but in terms of education. And maybe if I could just pivot to Charlie, because I think, you know, one of the comments that you made yesterday was how important it was for us, you know, as a community to enhance the pulmonary physiology training. But I'm going to give the floor to you.
Cindy, I really congratulate you on your programs. They're really amazing. David and Kaminsky and I I've been training people to do physiology and spirometry and for 50 years. And I think a couple of things that I reflect on. One of them is that I think we start too late in the training. We need to get earlier on in medical school. And so that's a topic for a longer conversation. But David Kaminsky and I did a study where we were training primary care physicians just south of the border in Vermont. Not a big study. We spent a lot of time and effort training them. And when we came back later, months later, half a year later, the penetration, the actual use was there. It was significantly increased, but it was pretty underwhelming, and the effect size is small. So, Sandeep, I'd like to ask you, I think you have the data in a very great way, but how do you know that all this training has resulted in permanence of utilization of first spirometry and then oscillometry? Because I think one of the biggest things, the hardest things to do is change how physicians practice medicine. I really think it's almost impossible in many cases.
Yeah,
Do you have any data?
No, you're absolutely right. It took me 20 years
Yeah,
to get spirometry into clinical practice. And it's a lot of hard work, and you
yeah,
have to be very consistent and persistent, and you have to simplify things, because if you don't simplify things, they will not use it. And
yeah,
if they don't understand how to use it, they'll not use it.
yeah.
So that's the challenge. I think it takes a long time, but
Yeah,
we have to make a start sometime, because otherwise it will never happen.
yeah, I agree. And Tom Petty took the same approach. He made spirometry real simple so that the average clinician would understand and then hence use it. So keep it up. Good job.
Thank you. Thank you.
And so the last question will go to a medical student, Misha.
Hi, Dr. Salvi. I just had a
Hi.
quick question, and it's kind of building on the other two. What time period in our medical education, do you think it's best to invest in training for oscillometry? Do you think it's during medical school? Do you think it's during residency? Or do you think it's once we go into clinical practice? Where do you think it's beneficial to intervene the most?
So spirometry is not yet taught in medical school, at least at the undergraduate level. That's the current state of the situation in India. But in the postgraduate medical training, so these are doctors who are going to be consultant pulmonologists. For them, spirometry is indeed taught during their residency. Now that is slowly increasing. Even until a few years ago, the spirometers were not widely available even in the teaching medical schools, but now they are. So that training has started. For oscillometry, I think it's a long way to go still. Oscillometry is a relatively new device, and I think a lot more research needs to be done until we really understand its true application. But we thought, why wait for those years until when the research starts showing good results? Why don't we at least start sensitizing people about the value of oscillometry? So we are now training pulmonologists across the country, and some of the internists who would like to take up respiratory medicine, doing it at the general practice level or primary care physician. I think it's a little too early for that.
Thank you very much. And in good oscillometry tradition, we're only 11 minutes late. It's after the first talk. So I'd like to welcome Dr. Disha Gopaldi for next section. She also comes to us from the Pure Foundation in India. And we don't yet have you on presentation mode. Perfect.
So wishing all a very good morning, and I bring you greetings from my organization, the Pulmocare Research and Education Pure Foundation in Pune from India. It's indeed a great pleasure and a joy to be amongst you all, and I would like to congratulate Professor Ron for a wonderful and a successful workshop, first day seminar yesterday, and I thoroughly enjoyed. It was a knowledge feast, and unfortunately we could not be present over there, but thank you so much for giving us this opportunity, a platform to present our work that we are doing in India. So the topic of my presentation today is prevalence of small airways dysfunction as defined by R5-R20 in the Indian asthmatic population. I've always wondered as to what portions of the airways are affected in asthma. And I've largely believed that it is the A and the B portions that are affected in asthma. Are small airways affected in asthma? Why is this an important question? It's important mainly because of two reasons. One, that it is likely to be manifested with a very distinct phenotype, which is very similar to COPD. And second, if the small airways are predominantly affected in asthma, the traditional medications of a mass aerodynamic diameter of 2 to 5 micron, is that treatment appropriate? So in order to identify these answers, it's very important to know that whether the small airways are affected in asthma. And to find that answer out, Professor Omar Osmani in the year 2016, for the first time through a systematic literature review, showed that 50% in 50% of the asthmatics, at least 50% of the asthmatics, the small airways are affected, whether measured by a spirometry, body plethysmograph, impulse oscillometry, nitrogen washout, or an HRCT. Small airways dysfunction, or SAD asthma, appears to be a distinct phenotype, which is characterized by difficult to treat, more severe form of the disease, uncontrolled asthma, nighttime awakenings, seen more in obese people, exercise-induced asthma, more prevalent in smokers, and seen more in females as compared to males. The drug deposition depends upon the aerodynamic diameter of the drug. So the drugs that are available at present, they range from a size of 2 to 5 microns, which do not reach the small airways. There are only 2 drugs that are available in the market. One is the Qvar by Chesi, and one is the Nivioli by the Cipla Limited. If we look at the drug deposition as per the Anderson cascade impactor, if we compare the traditional budesonide formoterol and ultrafine beclomethasone formoterol, if we look at the deposition in the S5, S6, and the S7 region, which represent the small airways, we see that the deposition of the traditional medication in the S5 region is 4.79 and 0.39 as compared to the ultrafine, which is 14.28 and 0.85. Similar patterns are seen even in the S6 and the S7. So with this, we can conclude that if a patient with predominant small airways being affected in asthma, they would be benefited, likely to be benefited more with an ultrafine formulation medication as compared to the traditional medication. The Atlanta study in the year 2019, which was done across 9 countries, was done to explore the relevance and the extent of small airways dysfunction in the asthmatic population, using a spirometer, body box, iOS, nitrogen washout, and an HRCT. And what was found was that the prevalence of SAD, as the severity of asthma increased, the prevalence of SAD also increased. They used the parameter of R5 minus R20 more than 0.8 centimeter water per liter per second, which showed a prevalence ranging from 50 to around 90%. They also used R5 minus R20 more than the upper limit of normal. But if you observe, if you notice that the upper limit of normal was not as sensitive as R5 minus R20 with a fixed cutoff. Therefore, this question arises, which is an appropriate cutoff value for R5 minus R20 to define small airways obstruction? Is it, do we use the more than upper limit of normal, or do we use more than 0.8 centimeter water per liter per second? To find this answer out, I did a literature search. And interestingly, I found a range of cutoffs that were used for R5 minus R20, ranging from 1.5 to 1. So this was a 10-fold increase. We also did a very interesting study and published it in this year itself, and we showed that the R5 minus R20 cutoff of more than equal to 1 is a highly sensitive cutoff with a sensitivity of 0.83, specificity of 0.62, and an overall accuracy of 78.5. Now, with this variability, this variation of R5 minus R20, what is the right answer? And therefore, my research question: what is the burden of small airways dysfunction as defined by R5 minus R20 among the Indian asthmatic population? And in addition, I also wanted to correlate R5 minus R20 with age, duration of asthma, severity of asthma with FEV1 percentage predicted, FEF 75% predicted, and area of reactance. My study method. How did I go about finding my answer? At Pune, we have established a network called the ARISE network, that is the International Network for Lung Oscillometry Research. Under this network, we have a group of 34 doctors, including pediatricians. These doctors are a part of this network and they help us answer our research questions on lung oscillometry. Under this network, we have our first registry called the LEAD registry. That is the Lung Oscillometry Registry for patients with various respiratory disorders as well as healthy subjects. So we collect data related to FOT, to iOS for healthy asthmatic, COPD, ILD, as well as other lung conditions. Under the study, we performed the oscillometry test using the Antlia device, which is an Indian make from a Bangalore-based company called the iCaltech. We could manage to collect approximately 8,000 participants' data who were asthmatic plus COPD plus healthy participants as well as other lung conditions. Of these approximately 8,000 participants, we picked up 1,000 asthmatics. Of these 1,000 asthmatics, after cleaning the data, we had 881 asthmatics who were eligible to be included in the statistical analysis. Describing my study population, the gender distribution. So we had more number of proportion of females as compared to males, 55% of females and 44% of males. The age distribution for male, the mean age was 45.6 with a standard deviation of plus or minus 16. Whereas for females, the mean age was 43.9 with a standard deviation of 14.1. To describe the lung oscillometry parameters for the study population, that is the asthmatic group, to highlight R5 minus R20, give us a median of 1.4 with an interquartile range from 0.9 to 2.0 for males and a median of 1.8 for females with an interquartile range ranging from 1.1 to 2.7. The median of R5 minus R20 in females was seen to be higher in comparison to the males. To find out the burden of small airways obstruction in my study population, I used different cutoffs. So I started with more than 1, then more than 0.9, more than 0.8, more than 0.7, and more than 0.6 for both the males and the females. In the male group, it was seen then that at least 70% of the asthmatics had small airways obstruction. And as the cutoffs decreased, the prevalence or the burden also increased. Similarly, for females, at least 80% of the asthmatic females showed the burden of small airways obstruction. And a similar trend was seen as that of males, that as the cutoffs decreased, the burden of small airways obstruction also increased. When I computed the correlation of R5 minus R20 with age and disease duration, there was no correlation that was noted. Further correlation of R5 minus R20 with the severity of asthma with FEV1 percentage predicted. So we could see a good step ladder pattern, increasing pattern, that as the asthma severity increased, the mean R5 minus R20 was also seen increasing. And with after computing the correlations, we could see a relatively good correlation of R5 minus R20 with FEV1 percentage predicted, with an R value of 0.5. Correlating R5 minus R20 with FEF 25 to 75. When I just computed the prevalence or the burden of R5 minus R20 with using a cutoff of more than 1, I got a burden of 76.7%. Whereas when I used FEF 25 to 75 with a cutoff of less than 70, got a burden of 70.4. And when I used a cutoff of less than 65%, I obtained a burden of 66%. When the correlation was computed, R5 minus R20 did show a relatively good significant with the FEF 25 to 75 percentage predicted. Correlation of R5 minus R20 with area of reactance, we got an R value of 0.6, which was relatively a good correlation. we got a range of 0.27 to 44.83 for area of reactance. And therefore, I thought probably it would be interesting to see if I compute the tertiles of this particular range and assume, or it might just potentially be the severity cutoffs for area of reactance or for AX in the near future. Just for instance, 0 to 15 could be mild, 15 to 30 could be moderate, and more than 30 could be severe. So to conclude my findings and to conclude the study, using a cutoff for R5 minus R20 of more than 1 centimeter water per liter per second, we obtained a prevalence of 70% in males and 80% in females in the asthma group. And as the severity of asthma increased, in terms of FEV1 percentage predicted, the R5 minus R20 values also increased significantly. A similar trend was also seen when we correlated R5 minus R20 with AX and FEF 25 to 75% predicted. And finally, small airways obstruction is highly prevalent among asthmatic subjects in India. This piece of information is very important in order for the doctors to prescribe the right prescription to the patients with predominant small airways obstruction, small airways being affected. And the way forward is we need to correlate R5 minus R20 with the HRCT findings, that is the functional small airways dysfunction defined by HRCT, to derive an appropriate cutoff value, or rather to fine tune or to polish the R5 minus R20 cutoffs that we've obtained till date. So thank you very much, and questions are welcome.
Thank you very much. And if you could stop the screen share, then we could put you and everybody else. Perfect. So I thank you very much for that talk. I think the concept or the need to actually define cutoff values from which we can hang a diagnosis on is probably something that's going to keep a lot of us in business for many generations to come. And my one editorial comment is I think part of the problem, particularly in the sort of definition of small airway obstruction, is that we have yet to have a really good gold standard diagnosis from which we can hang our hats on. So I'm hoping that I see that Julian, you actually have your hand up already. So why don't we start with questions with you? And I'm hoping that this will generate actually a lot of discussion from the group.
Thank you. That was an absolutely elegant presentation. Thanks so much for that. I think that in pediatrics, obviously, we're going to have to, it seems like your criteria were more robust if you used an absolute value for R5 minus 20 as opposed to an upper limit of normal. And obviously in pediatrics, that would not apply because children are growing, so that you won't be able to use an absolute value. You'll still have to use an upper limit of normal. Do you have any idea why you think the absolute value is more robust than the upper limit of normal?
For the pediatric population?
Yes.
So, when we went through the literature review, we've seen that for different age groups, you require a different cutoff value. And most of the literature that is available have used a cutoff value. I may not be in a position to tell as to why an upper limit of normal may not be appropriate for the pediatric population. But as of now, what we are seeing even in our study population is that cutoff value for age group, say for 10 to 15 would be a single cutoff, then 15 to 17 would be a single cutoff, would be more appropriate.
What was the youngest age that you looked at?
So the younger you are, the higher would be the the values, the resistance values. As your age increases.
In your study, what was the age range? What was the youngest?
So the age range for this particular age group was starting from 20 years.
Okay. Thank you very much.
Laura, I know that you've been doing a lot of work in this area, and I see that your hand's up. Perhaps you can weigh in.
Hi, everybody. Thank you very much. I love your presentation also. And hi, Dr. And it's very nice to see you from Mexico. Yes, I just want to ask for your permission just to show one graph that I have in my computer. Is it possible?
Yes.
Yes. Okay. We perform some reference values for adults and children's, and I just have this cutoff points for R5 minus R20, but I think probably we really need to use also a Z-score or a equation, because it perfectly, we can see here that if we use this cutoff point or this cutoff point, we are going to have some false negatives. Well, but these are healthy people, right? So I don't know if in the future we can use the things that you find against this. And but this is what we saw with our healthy people. So that's what I want to show you, and congratulations. I love your presentation also.
Thank you so much, Laura.
So thank you very much, Laura. Ron, would you like to comment?
No, I mean, I think we're on the money, Chung Wei. This is going to be a lot of work, and I think it's primordial that we get to it, because it's the obvious question the clinicians are going to be asking. They're going to be saying, you're telling us to deploy it, but you're not giving us cutoff values. In the absence of consensus in my own practice, and independence, but happily in agreement with Brian Lipworth, I came up with the absolute cutoffs that agree with his, and I find them just empirically in my office very useful. But we need somebody to actually take that that absolute cutoff, and I'm reading for the AX, for example, 10 centimeters of water per liter, and because it's non-normally distributed, we're doing doublings from that to classify people as normal, mild, moderate, severe. Then mechanical heterogeneity, having been ventilatory heterogeneity, thanks to the work of Rachel Eddy and Grace Paraga, amongst other people. And I actually got that published without any validation, which is a bit of a shock. But there it is, it's in the literature, and it's the only one that I know of. So whether it's that or another proposal, we need to adopt it into a real trial and look at it more scientifically. And so that's the challenge I throw out. I don't have an answer, but I see possibly a way forward. I don't know if this will generate discussion from other people around how they would approach the same problem, but I would be very eager to hear today.
In one, smaller population, if we are now collecting oscillometry data, but we have a population of people that we think have, whether it's asthma with small airways, it's not just asthma with small airways disease, but also this small airways disease, distal lung disease, that's biopsy confirmed by that surgical lung biopsy. That's been an issue. Like, what is the gold standard for that? So in some of our patient population, we have lung biopsy, so it'd be interesting to have, and we do have some oscillometry data on that. It's not huge numbers, but to maybe try these different cutoffs and see like which ones, that's one.
It comes to mind a data set that already exists, is the one curated by Grace Paraga in London, Ontario, and Rachel, I just put it out there, so I'm going to pick on you and call you out. We had played around with, they played around with different cutoffs of different parameters. I know AX, and I think you may have played with R519. As I recall, it may have been disease specific, but the cutoffs that were appropriate for COPD population might be different from those that were appropriate for asthma population. I was wondering if you could just turn on your camera and comment on that.
I'm on my phone and moving around, so I can't have my camera, but I can respond, and I'm happy to respond. I unfortunately missed part of the afternoon yesterday. I don't, with the virtual meetings, I always have good intentions, and then other meetings come up and other things. But yes, you're absolutely right, Ron. It was a ATS abstract, and I think we had relatively large cohort still of asthma and COPD against age-matched never smokers. So these are slightly older people too, but indeed the threshold was a little bit different, and that was looking against some measurements with MRI as well, but indeed the thresholds were different for COPD and asthma.
And I think perhaps it really is a call out for really more work in terms of, normal reference values and normal data from normal healthy people across countries and across ages and sex. So thank you very much. That was great. It was a great talk and generated some great conversations. So, and we're going to move from a virtual presentation to an in-person presentation by Andy Kiemelin, who is a PhD candidate from Brussels, Belgium.
I think it's something first need to pick up.
All right, thank you for the introduction. Good morning, everyone. So to introduce myself, I'm affiliated to the electricity department of the engineering faculty of the Vrije Universiteit Brussels. So the presentation is also a bit more technical oriented. Research is about the validation of a novel low-frequency oscillometric measurement functionality implemented in a mechanical ventilator. The research project is a collaboration. Opting fine, or
We're not seeing it on the internet, so let's
All right.
fix this up so that we're all on board here.
At the top,
Well,
stop
here we
sharing.
go.
Yeah,
Yeah,
share.
Start sharing at the top, right in the middle.
Okay, so this is
Middle.
what we
In the
want.
middle at the top.
This one?
Oh,
No.
top.
Oh, stop sharing. Yeah. Sharing the wrong screen. Thank you. Okay, so now let's go to your screen. And this is your talk. Okay. And this should be good to go. And this is going to put this there. And, oops, what's that? Oh, this is your. If I go, that's okay.
all right, excellent. Thank you.
Okay, Roger.
Wonderful. So I was saying that it's a collaboration with Professor Jonkheer, he's head of Department Intensive Care of the University Hospital of Brussels, and also our industrial partner Demco Maccabi Respiratory System, who produces blower modules for mechanical ventilators. Now, the context of the research is intensive care units of a hospital. It is in the domain of monitoring techniques of mechanical ventilated patients that our research may have its benefits. The challenge that physicians are facing is that the current standard of care measurement tools are of invasive nature and will require total patient passivity to be accurate. This issue, a prime example of this issue is research conducted last year by Taufik et al. They were comparing different technical implementations of those standard of care measurement tools, but out of the 600 measured patients, they could only use data of 10 of them, mostly for 8% due to patient activity. Now, with respect to the standard of care tools, we are considering the static compliance estimation via a low flow PV loop, as well as the dynamic computation of the compliance and resistance via fitting of the differential equation to the ventilation waveform. And it's against those two measurement techniques that we will compare our solution to. And of course, our solution deals with oscillometry, otherwise I wouldn't be here. Now, what we're trying to do is to get the R and C, the same mechanical parameters as standard of care, and make them comparable with our oscillometry results via using a low frequency oscillometric excitation signal. Now, measuring the same low frequency region, well, the problem boils down to dealing with patient and ventilation disturbances in this low frequency region. Solution that we propose is to use an adaptive excitation signal design strategy. The novelty of this is that we will extract the same R and C in this low frequency region as the standard of care tools via the application of a dedicated low frequency multisign. Now, when we go look at how we implement this solution, well, first we have on the left the mechanical ventilator, which was a CE certified blower, which is being used in Dutch hospitals. We made some software modification to allow to apply an oscillometric excitation signal, but the total oscillometric procedure is controlled by an application made and installed on a separate laptop. Over there, the operator can design the excitation signal, load it on a USB stick, and then we can go and execute it on the ventilator. Back on the application, we can also perform automatic analysis and look at the graphs as one can expect. Now, to design this total setup, a certain number of design requirements need to be taken into account. First of all, of course, we cannot cover the monitoring screen since vital respiratory parameters are being shown there. And that's why we reduce the total oscillometric controls to one button. It's a dynamical button where the operator can activate and deactivate the procedure, but it will also show the status of the experiment via a dynamical text display. Second requirement is we cannot disturb the ventilation waveform since proper oxygenation still need to be able to achieve. Therefore, a limitation of the peak-to-peak or excitation signal to ensure still a proper ventilation is achieved. Now, on the graph, you see in blue the original ventilation waveform, in orange the waveform that results after superposition of our excitation signal. One can see that still a proper ventilation signal is achieved. Now, last, to enable this comparison with the standard of care estimators, we will also need to use the same single compartment model. I'm assuming all of us is a bit familiar with this model. It is conduct, the balloon seal over it, and the behavior described by the equation of motion of breathing displayed here. And later on, in one of the slides, I will continue on this model. Now, with all our technical requirements in place, we can go take a look at the design of the multi-sign excitation signal. The basis is a multi-sign consisting of a sum of cosine, each having a defined amplitude, frequency, and phase. Now, since the novelty that we propose deals with the design of the frequency vector, I will start with that parameter. Now, the total idea to measure in the low frequency region deals with the spectral separation between the ventilation frequencies and the excitation frequencies. We will place the excitation frequencies on those locations with the least influence over the ventilation frequencies and its harmonics, taking into account certain ventilation variations due to patient activity. That is the idea. Certain practical steps need to be taken to realize this idea. First, we need to ensure that the ventilation and excitation frequency are harmonically relating. This is ensured by ensuring that their division with the frequency resolution results in an integer number. Graphically speaking, when we draw the line graph, every multiple is a line on the graph, meaning that they are harmonic relating results that they will be placed on each of a line. Now we will further improve this relationship via demanding that the ventilation frequencies are put on the even lines, on the even multiples or frequency resolution. When we do this, their harmonics, their nonlinear even contributions will all put on also even lines, meaning that when we select odd multiples, they will not pollute our excitation signal when it's on those odd lines. Now, currently, just selecting odd multiples of frequency resolution doesn't ensure any, there is no disturbance via ventilation variations, and therefore we ensure a certain region around the ventilation harmonics to not being taken into account. Now, from the remaining spots on our frequency grid, we can select 8 or less evenly spread candidates for our excitation signal. With our excitation frequency designed, we can go take a look at the other two remaining parameters. First, we have the amplitude, where we choose an exponential decreasing distribution over the frequencies. And for the phases, for each sign, we will select the phase with the best crest factor out of 1,000 generated uniformly random distributed phase realizations. That is our excitation signal. Now let's take a look at the total measurement procedure. First step is making this measurement of the ventilation waveform such that we can design the excitation signal on the application side. The excitation signal details will be saved on a USB stick and transported back to the ventilator. Over there, operator can activate the arrow experiment. Measurements are saved on the USB stick. Measurements are conducted via pneumatograph with the differential pressure transducer. Measured on the USB stick, going back to the application, there we can perform the analysis. Now for this analysis, there are two steps remaining. First, the verification of the measurement accuracy via coefficient of variance of the non-parametric impedance estimate. At every line, we check if you still have 10% or lower. And then the last step is about processing. We will calculate the parametric impedance estimate to determine an R and C by rewriting the single compartment model in its regressive form, with S being the Laplace variable and theta being the parametric vector that we want to estimate. Therefore, certain number of assumptions need to be made. First, we assume that our measurements are disturbed by additive white Gaussian noise. Second, we assume that the noise is uncorrelated over the frequencies with circular complex at the frequency. And last, we assume that the parameters converge to a normal distribution. Now, to determine our parameters, we will minimize a weighted least square cost function V, with W being the diagonal matrix of the inverse of the variance of the error vector. But due to the dependence of the variance on the parameters, a two-step minimization approach is used. First, we will minimize a iterative weighted linear least square, which is biased for noisy H, and our flow is certainly noisy, and therefore this will be used as a basis for a weighted nonlinear least square estimation. That will result in our R and C, and when we validate the total estimation procedure on a simulation, we could see that the parameters converge to the real value, which is great. But now let's take a look at how it actually performs. We have measured the ESA 5000 in a number of configurations. It's a long emulator where you can choose the resistance and the compliance value. For the first, we choose 20 and 50 for compliance. When we look at the spectra, we can see that the spectral separation between the ventilation frequencies on top, the yellow crosses, and the excitation frequencies, the purple circles. So spectral separation achieved. That is great. Let's take a look at the non-parametric and the parametric estimation. On the graph on the right, we can see that the proper model fit is achieved with a relative error of the resistance of 4.8% and for the compliance 1.9%. Now, when we compare our technique in the light orange at the bottom with the standard of care approaches, we can see that for the resistance, we have the best estimation, and for the compliance, the second best. Look at the coefficient of variation for both parameters. For the resistance, we see that we have a decent result. And for the compliance, we actually see that we are the worst. It's still below 10%, but actually we expect it to be even worse, given the fact that the other techniques use the ventilation signal or a similar signal, which is much of higher energy content compared to our arrow signal. But using the ventilation signal make you dependent on complete patient passivity. Now, looking even further and looking at the application during more supportive ventilation modes, where more patient activity is prevalent, we can see that we're still able to get a decent estimation. The ESA 5000 emulated a resistance of 20 and a compliance of 100, and we can see that we still achieve decent results, especially where the compliance estimate of the standard of care tools are completely failing, which is a nice result. Now, to conclude, we have shown that we achieved a proper resistance and compliance estimation via the application of a low frequency excitation signal. We have achieved comparable results with the standard of care via the application of a spectral separation technique. Now, the main benefit is that we are less disturbed by patient activity. It's a patient-friendlier technique and it's easier to use. And future work involves the validation on a wide range of test loads, but also looking at more different kind of simulations of this patient activity, as well as determining the small detectable difference of our parameters. Next, in September, we'll also start equivalence trial on 21 intubated patients to also look at the feasibility in the clinical practice. Before I leave the floor to you all, I first want to mention if anybody's interested in the techniques presented or in the devices developed, feel free to contact me. And now I'm looking forward to your comments and questions. Thank you.
Thank you very much for that great talk. I'm so short, I can't see the audience. So
Jeff audience.
stop sharing for a moment and put everybody on the gallery. So do we have any questions, Jeff?
Really interesting talk, and it's a novel approach to measuring mechanics. Many ventilators offer the ability to measure mechanics from the ventilation waveform, like they'll give you compliance or even resistance sometimes. And they're using the ventilation waveform, whatever it is, right? Just to get the two numbers, right? And which is interesting because they're using a large amplitude swing in volume at the frequency of breathing. And you're choosing to squeeze in, which is really neat, small amplitude oscillation in between the harmonics of the primary ventilator waveform. Have you compared the resistance and compliance that you might be able to, you should be able to use your exact same technique from the ventilation waveform to the interleaved oscillometry waveform that you put on? Right, because the ventilation waveform, it's not a sine wave, but it's a you know almost square wave type. You can get resistance and compliance from that.
Yeah, from the ventilation waveform itself.
Exactly, and now you're getting resistance and compliance, but I guess at a different frequency range. Have you compared or used that on the same plot to see if it agrees? Because it's a large amplitude waveform versus a small amplitude waveform that's varying during breathing.
Yeah, indeed. So not the completely same algorithm has been used, because for the ventilation waveform, we used the CE certified ventilation waveform as our comparable standard, which is implemented in the Temcon device itself. And there we can see that, especially during the controlled ventilation modes, is achieved decent results. And one would say, yeah, no point of applying an extra signal when it achieves good results. But the thing is that it fails when there is certain activity popping up. And that could be shown when the two tables were being displayed, that one can see, okay, during controlled ventilation, good results, but during the support ventilation and the more patient activity is involved, the worse the signal it gets, the worse the result gets. So it's over there when you're trying to get the same result, but across multiple ventilation modes, that there can be a benefit for error. But indeed, during controlled ventilation modes, it works fine.
Because then it's predictable.
I would think, just a quick comment, like when the patient is doing inspiratory efforts while you're ventilating, I would think that still the imposed oscillations that you're doing would also possibly be effective, possibly less, because it's at a different frequency range, but they still would be perturbed.
Yeah, well, so the perturbance mostly is due to the high energetic signal, and you can see it via the, as you call it, leakage, that the ventilation harmonics is getting more and more noisy and noisy. So the disadvantage, and it's what we also still need to investigate, so we are putting it in between ventilation harmonics, but the more activity, the smaller this can get. And then it's the question, how much activity is needed when we fail? So that still will be determined during the whole load of mechanical test loads to see if it's a wide range of activity or not. So it's a very good point.
Zoe?
I
And then I know Ramon, I saw Ramon's hand up, and so we'll go Zoe first and then Ramon after that.
So I had a couple of questions. Nice presentation, Andy. What's the lowest frequency do you think you're going to be able to discern?
So the thing is that we are looking at it as a cost. The lower frequency you select, the more it costs, because our energy is limited.
Yep.
So now we're also looking at more choosing the frequency with respect to their costs, despite take just 6. But technically speaking, we are able to go to 0.1.
Oh, wow.
But it will really depend on achieving still the 10%, and therefore some choice will be made. But that will be done with respect to the model used.
The other, in your planned trial of 21 intubated patients, what kind of patients?
Those will be very, what we can get, but they're a little bit different. We are not looking at any clinical picture. So we're only looking at the compliance and resistance estimate across their journey in intensive care unit. And therefore, more different they are from each other, the better it would be for us.
Yeah, yes and no. I mean, I'm really piggybacking on just you're looking at small volume perturbations on the big ventilator, and you've got a patient in the ICU with ARDS, and they're going to have highly linear, loops, just breathing loops. And so you're going to get all kinds of numbers depending on where you are in the breathing cycle. I mean, I might start with simple, abdominal surgery type of things where the lungs are normal, just make sure things are working the way you think they are.
Yeah.
Because you're going to get a lot of noise once you start getting into patients with sick lungs.
Yeah, well, I know we have certain number of inclusion criteria and exclusion criteria, but as an engineer, it doesn't say a lot to me. But, but it's a very
the last redoubt of sound. Yeah,
it's a very, very good question. I'm gonna put it on the board.
Lay this on your clinical colleague.
Exactly.
Last, the clinicians become used.
Yeah.
I'm going to just go to our virtual audience. So I know Zoe, you've got your hand up for a while. So Zoe.
Thank you. I joined with my question to Jeff's and also Charlie's. So it's a very good idea. We tried to do something similar, but the respirator was the boss, and it was triggered by the patient or the dog or whatever, and it couldn't maintain a rhythm in which you can find the values to impose your oscillatory components in. Anyway, that's my problem. In this ideal setup, when you are testing this device with the RSL 5000, which is a great device, but it is very, very linear. It's totally unlike most of the patients who are under respiratory support, invasive respiratory support, who are on the verge of recruitment and de-recruitment. So eventually, with this small probing signal, which is spectrally separated from the artifacts, that's a ventilator activity. This gives you an average impedance and does not reveal what happens inside the breathing cycle. So that's one question. The other one, when you encounter your impedance spectra from 0.1 hertz and some harmonics, you will be given a nice material to fit with low frequency impedance models, like we heard yesterday from animal experiments. So that would be great to fit a more sensible model which reflects both the tissue and the airway compartment mechanics in one spectrum. But probably Bela, who is following you, will give other good ideas. Thank you very much.
Yeah.
And congratulations.
Thank you. Thank you for your comments. First, with respect to the intra-breath, it is possible, and we included it in our clinical trial. So we apply 5 hertz signal. We will also do that measurement because given its interests. But the main reason why we choose the RNC is because our physician is used to those values with the standard of care tools and can have directly relates to it. So that's one of the reasons why we have chosen to go as similar as possible to the RNC. Now, with respect to the that also relates a bit to your question about more precise models. That's one of the reasons why we use a single compartment model, but indeed we can improve towards more detailed models and also improve our excitation signal towards a model of interest. I hope that answers your question because I'm not sure if I completely understand all of it.
That's okay. So that was my point.
Okay.
I only worry about what new information you get in addition to what a normal up-to-date respirator can tell you about RNC.
Well, so the thing is that we will be able to maintain the RNC calculation across different ventilation modes. That's the novelty, where in pressure support mode, the current solutions are of very invasive nature. So with respect to insight into the respiratory system, less novelty, but maybe there will be any beneficial with respect to extubating, when you still be able to get the available RNC. But those are questions for more clinical oriented people.
Okay, thank you.
Thank you for your talk. So I have a practical question. So how about no invasive ventilation? So most of our patients are COPD here in Montreal, and the majority of times so we use the no invasive ventilation. So did you measure the parameters like the oscillometry on these patients without intubation, so only no invasive ventilation? Because a lot of time we have mask and we have leaks.
Yeah.
So
yes, but first, so we have designed the setup for intubation, and also look at the 4 different modes that we have available. It's the controlled, pressure and volume. It's also pressure regulated volume control and pressure support. The pressure support is, I think, the one who relates most to the non-invasive ventilation you use. And over there, we are able to get good values. Now, also beside that, we unofficially tried on myself with a mask, and that is possible, but results are less due to the more leaks and those factors, but possible.
yeah.
Thank you very much. And I think we'll look forward to hearing more from you over the next couple of years. So this is indeed a great segue to Dr. Belisuk's talk. And are you there?
Yes, I am here.
Perfect. And,
can I start sharing?
Yes, please. And if you could go on to the presentation mode. Perfect.
Okay. All right. So first of all, thank you very much for, especially Ron, for organizing the meeting as well as accommodating my last minute request. I would like to talk to you about a method that we developed basically a couple of years ago. It's also low frequency impedance measurement, but in contrast to the previous talk, we will actually try to utilize the mechanical ventilator provided signals in a specific type of mechanical ventilation that we call variable ventilation. And these are the authors who contributed some of the, in fact, most of the data have been reported in this scientific report paper. So, okay, all right, so sorry. Yes, so I don't think I need to talk about the original study introducing the forced oscillation technique by Du Bois and colleagues, but I'd like to mention a landmark paper basically by Zoltán Hamtos in 1986, where he measured low frequency impedance basically around the spontaneous breathing rates. And I was fortunate that at the beginning of my career, I was actually a part of this study. So interesting features include frequency dependence of resistance and compliance, There are, however, some limitations with this because measuring the impedance around the breathing frequencies is a challenge since especially we have just seen from the previous talk, you have to be careful about where the frequencies are. So the forced oscillation technique itself can interfere with breathing. And generally speaking, you need some sort of specific equipment to apply the pressure oscillations. So let me then change topic for a moment and introduce variable ventilation. Variable ventilation is a relatively new approach to mechanical ventilation that was introduced in 1996 by Lefebvre et al. From Alan Muchie's laboratory in Canada. And what they did was that they used pigs ventilated with conventional mechanical ventilation, as well as a mechanical ventilation in which the tidal volume and frequency change from cycle to cycle. They sort of try to give back the natural breathing pattern to the mechanical ventilator. And what they found was that both compliance and gas exchange improved in a acute lung injury model. Soon after that, we actually proposed a mechanism for this, which is based on the recruitment along the nonlinear pressure volume curve, regional pressure volume curve of the lung. And then since then, we and others have published a large number of animal studies showing that variable ventilation improves gas exchange. Actually, it alters the biology, for example, promotes surfactant production and secretion, and it also reduces ventilator-induced lung injury. A couple of studies actually used also variable ventilation clinically. For example, Boker et al., also from Alan Muchie's group, showed that in subjects undergoing surgical operations, abdominal surgery showed improved gas exchange and respiratory mechanics. Later, it was shown that variable ventilation improves patient ventilator synchrony as well as reduces inflammation. What does it have to do with low frequency impedance? Well, we also implemented variable ventilation on the Puritan Bennett 840 mechanical ventilator. Here is a screenshot showing the tidal volumes here, and you can see that some of the tidal volumes are low, some are very high. But interestingly, also, we actually programmed the ventilator in such a way that the respiratory time was proportional to tidal volume, inversely proportional, meaning that the frequency of breath is high when the tidal volume is low. And that means that we could actually maintain a constant minute ventilation from cycle to cycle. So as you can see, this respiratory time is short, the tidal volume is short, this respiratory time is long, the tidal volume is high. And hence, variable ventilation naturally induces variations in frequency. This made us hypothesize that variable ventilation can be utilized to measure low-frequency respiratory mechanics during patient ventilation, but without requiring any additional setup. As you can see, the impedance carries frequency dependence, and variable ventilation is producing this basically the variation in frequency. And we have this very simple equation. ZVV is called the method that I will show, and this is equal to Z plus VV. How does it work? Let's first look at what the data are. We had a FDA cleared small clinical trial, and then we collected data. This is the protocol. 5 patients with mild ARDS were conventionally ventilated for over a day, And then at the time of the protocol, they were placed randomly either on conventional mechanical ventilation or variable ventilation for 3 hours, followed by a conventional ventilation of 1 hour washout period. And then the patient was switched if it started with variable ventilation in session 1, then it would be conventional or vice versa. Here are the data. These are 2 cycles in one of the patients, and these dots show the beginning and the end of the breath cycle. And then we isolated these cycles and then applied DFT and calculated the DFT of the pressure and the flow waveforms, and then calculated impedance as the ratio of the two. The real part is, of course, the resistance, and the elastance is just -2 pi times the respiratory rate times the imaginary part of the impedance. This is a plot of all resistance values here. As a function of breath numbers. So 1,500 breaths were applied in this case, and then these are the different frequencies. This all shows that there's a lot of variation, and it does not show any clear pattern. However, if we plot the resistance against the frequency, then some pattern is appearing. And in fact, next what we did was actually we actually split the frequency range into bins and then averaged all these resistance values in each of the bins separately. And then what we got is that a clear frequency dependence of the resistance. This is fairly interesting. And so we looked at more carefully the data. This is now showing we split the 1.5 hour variable ventilation to the first time section, which is 1.5 hours, and then the second is also 1.5 hours. So sorry, the total was 3 hours. And then we looked at the frequency dependence of resistance in the first section and the second section. And what we can see is that there is a clear drop, but the frequency dependence is about the same. Yeah, we looked at the elastance again for the first 1.5 hour during variable ventilation. We get this elastance in one of the subjects, and then there is a drop in elastance and also a slight change in frequency dependence. We can actually bin the data not only according to frequency or time, but also according to tidal volume. And this shows you that in that first segment, the elastance did not depend on the tidal volume. V2 is this one, is larger than V1, 2 bins for tidal volume. And this is what we found for the second segment, which is that, first of all, there is a big drop in the elastance that corresponds to this drop here. But then increasing tidal volume actually increased the elastance, suggesting that maybe the patient was already closer to the top of the pressure volume curve. These are the data for the resistance. Against, in this case, there is an increase with tidal volume of the resistance, and then the same happened in the second session, but the whole data dropped by about this magnitude. We found very similar patterns for the subjects, and without going into all these numbers, all I want you to focus on are the p-values. So these are differences of resistance and elastance down here between the first segment and the second segment within the same subject. And so each row is one subject. We can see that resistance decreases except for patient 3. Elastance significantly decreases in all of the patients. So what does it tell us? Well, our method ZVV assessed low frequency respiratory mechanics effectively in all 5 patients. And it provides also evidence that the patients benefited from the variable ventilation. To make sure that what we measure is not artifact, we also used a mouse model of acute lung injury. And in this case, the mice were lavaged. At first, the protocol shows that we started ventilation with the variable ventilation for 10 minutes. Then the mice were lavaged, and then we applied another 20 minutes of variable ventilation. And then we evaluated again resistance and elastance. I'm just going to focus on the elastance here. For the first section, we divided it into two 5-minute long periods, and then there was no difference in elastance as a function of frequency. During the second section, in the injured lung, variable ventilation actually lowered the elastance, not by a lot, but still statistically significantly. Now, one might ask that, well, what happens with this calculation from a single cycle? And indeed, one problem is the effect of transients. To examine this, we developed a computational model. Here is a Kelvin body with one spring, another spring, and dashpot in series in parallel with this single spring. And then we stitched together sinusoidals of different amplitudes and frequencies. And then this Kelvin body was drove in the computer model with this volume signal, and then we calculated the pressure response here. And the dashed line shows you when the model is in steady state after, for example, applying one of these sinusoids for 10 times. However, if we continuously measure the pressure response, we find this continuous line, as you can see, that it varies, and there is a clear effect of the transients because every cycle has a different frequency and different amplitude. So we actually solved analytically the Kelvin body, and the analytic solution suggests that there is a steady state solution, these two parts. This is just the standard linear equation of motion. And then there is exponential terms for the transients. What you can see here is that this is the same data as before, but I would like to focus on this particular cycle here. You can see that the beginning and the end of the cycle do not match, not unlike in the case of the steady state response. So we came up with a very simple correction factor, which is that basically the correction depends on the respiratory rate as well as the difference between these two pressures. And then also subtracting the offset, and then we recalculated the resistance and the elastance, and then what we found was pretty interesting. First of all, for elastance, the error was not too big. For the resistance, however, the error, you could see that before correction, the error goes from about 20% at low frequencies to all the way minus 40% at the higher frequencies. After correction, the error drops below 2%. So this is good news, and it suggests that this simple correction allows accurate estimating of the steady state oscillatory parameters of the system. So to conclude then, we have a novel technique for clinical and research-based assessment of respiratory mechanics. The advantages are that it does not require interrupting mechanical ventilation. It provides assessment at the breathing rates of the mechanics, and it does not require any additional equipment. However, one important thing is that these data also demonstrated that this mechanical ventilation that we call variable ventilation actually improves the ARDS condition as well. And combined, the VV, when combined with impedance that we call ZVV, can be both diagnostic and therapeutic. Thank you for your attention.
Thank you very much. And if you wouldn't mind stop sharing, I see that Jeff has raised his hand. Jeff.
Yeah, Bella, hi, long time no see.
Yes.
That was a fantastic talk, and this looks to be very important to me. So I think congratulations. This is really remarkable data. And excuse me, pragmatic as well. Excuse me. I would just like to suggest an alternative interpretation. I mean, you used a Kelvin body. I'm always really skeptical about those kind of lump parameter kinds of models, particularly in the low frequency range where we know that, based on a lot of the earlier literature, like Baylis and Robertson, that just representing tissue resistance as a viscous resistance just isn't right. So two questions. One is, have you actually made pressure volume loops so we could see what the pressure volume loops look like? And I think that could be very instructive. Second, I did a back of the envelope calculation about, instead of using a Voigt model, what if you just said there was a tissue hysterosivity that accounted for the resistance and maybe a little bit of airways resistance? And it comes out, you come out with a hysterosivity that's right in the physiological range. So the frequency dependence of the resistance has to do with a tissue rheology, but it's got nothing to do with a Voigt body or a Kelvin body or anything of the sort. So I'm just wondering if you looked at that, because I think you could fit your data even more simply with just saying that there's a tissue hysterosivity. But anyway, that's my thought. And you may not have thought about that, but it looks to me you'll get an eta of about 0.2, which is just what you'd expect.
Yes, so thank you. This is a great comment, and we did think about this. However, when you combine tissue resistance, whatever model, you could use the constant phase model, or but then there is the notion of heterogeneity, and unfortunately, heterogeneity in the disease lung can mask that particular characteristic tissue resistance or long resistance behavior, the frequency dependence. That's one issue. The other is that I acknowledge the Kelvin body is not the best choice, but it has a big advantage because we were able to calculate the transient response analytically, so we exactly know the result, which actually prompted us to find out how to correct for the effect of the transients, because we get the impedance from single cycles, and the FFT method naturally assumes that you have already employed like 10 cycles and you are in the steady state. And so that was our primary reasoning. The other question about the pressure volume curves, that's a great point. We have not looked at that, but we should. I agree.
Good. Thank you.
We'll go to Jason and then to you, Zoli. So Jason first.
Well, great talk, Bella. I'm familiar with your work, so I've heard this before, but it's great to see it in such finished form. One thing I wondered about was whether you might want to, when you're interpreting what's happening with your ARDS patients, think a little bit more in terms of de-recruitment. Because one thing that maybe, I'm going to suggest that maybe the major effect that you're having on the lung with variable ventilation is you're more effectively recruiting the lung. And that would reduce its compliance. And I also noticed in the second half of the data, if you look at elastance, at the highest frequency, it started to go down, which suggests the effects of inertance are beginning to manifest. And so you could have opened up the lung enough so that you don't have a very high elastance, which is masking those effects. The other thing, which is easy to say and harder to figure out, is what happens if you have recruitment and de-recruitment going on during the breath, because you have fairly big breaths. I did an analytical analysis of a very contrived situation about 12 years ago, looking at how ongoing recruitment and de-recruitment during the breath might affect impedance. And it definitely does have an effect. And basically, the effect can be anything you want, depending on how you think the recruitment and de-recruitment is going. So it's a bit complicated. But anyway, just something to think about. I think if it's ARDS, you got to think about recruitment and de-recruitment.
Yeah, all good points. I should say just that basically the advantage of I did not talk too much about the disadvantages. There are some, but the advantage of the method is that you can actually bin the data in 3 different ways, which we have done, which is that in time to assess the effectiveness of the mechanical ventilation. You can then bin the data according to frequency as well as partitioned in time, so that you can look at, for example, the effect of heterogeneity or hysteresis. And then, but you can also do this binning according to tidal volume. And so, and the results are varying. So in one patient, and I think this is a good point because in one patient, we saw that the tidal volume dependence of the elastance increased. That is to say, using a higher tidal volume, we got a higher elastance. And that means that we probably were already close to the top of the regional pressure volume curve in that particular patient. In another one that maybe I don't remember correctly, but in any case, certainly in the mouse studies, we saw the opposite, suggesting that the mice was ventilated in such a way that we were far away from the plateau of the pressure volume curve. So a decrease in elastance due to tidal volume is an inverse nonlinear dependence of the tissue property.
Right. Actually, that was the other point I remember. But again, I come back to recruitment, because if you had a lung that was recruited while you were ventilating it, the elastance is going to go down.
Yeah. So the mathematical model that we published back in 1998 is exactly how recruitment is influenced. How the amount of open lung is influenced by the variable ventilation along the nonlinear pressure volume curve. And if you place the PEEP correctly somewhere in such a way that you are actually
Oh no.
Pause for effect. Yeah.
Well, actually, while we had at a dead spot, could I just jump in on your comment, Jason? It turns out if you go back and you look at the original hysterosivity paper, Fredberg and Stemenovich, 1989, we show that I'm endorsing what you said. Recruitment, de-recruitment, the natural description of that is the hysterosivity, and we give the argument for that in that paper, which is like 40 years ago. So if you're arguing that it's recruitment, de-recruitment, the natural description of losses is hysterosivity. Too bad Bellas hasn't heard that, but there you go.
Yeah, right.
Well, in any case, maybe you are right. What I can tell you is that we measured a bunch of mouse data, and it is consistent with recruitment along the nonlinear pressure volume curve. And that opens up the lung. And maybe one should look at, the losses as well. But the data also suggests that in the whole lung, this is part of how variable ventilation improves lung physiology. It opens up the lung.
Right. So I'm going to give the last comment before coffee to Zoli.
Thank you. A very short comment. So I think we are not seeing a little devil in this setting. The endotracheal tube.
Mm-hmm.
The patient is ventilated, and the resistance values which you showed is actually 2/3 from the ET tube with its huge orifice effects both ends and huge nonlinearity. So this is shifting the whole resistance curve up, and behind this biasing effect is almost completely irrelevant whether you use a Kelvin body, Voigt body, or a constant phase model behind. So I think it is a very, very important component, very high degree of nonlinearity depending on the tidal ventilation flow pattern, basically. And just a very short question. In this pooled huge amount of data in the human measurement, did you find any spectral sign of the cardiac contribution of the pressure and flow?
Okay, so I'm gonna be try to be short as well. First comment: endotracheal tube is very true. All I have to say is that actually the physicians who I worked with, they told me that, wow, if there is a sudden decrease, for example, of the resistance for whatever reason, one thing that they think about immediately is that maybe something cleared, part of the endotracheal tube. There could have been mucus or whatever in it, but you are completely right. Cardiac. So we thought about all sorts of possibilities, including spontaneous breathing. So when the patient fights the ventilator, that is a much bigger signal than the cardiac. And because we have, in every frequency band, we can have hundreds of data points, and a few, when the cardiac falls in that frequency band, will not affect the results. It's very robust.
Great, thank you.
So thank you, everyone, for that great discussion. I think a lot of these physiology discussions are very helpful for a lot of us who, there are actually, I think, a number of people in the audience who probably weren't born when Dubois actually published his first paper. So we're going to break for coffee, and we're going to take maybe a 15-minute break. Ron, is that okay? So we'll reconvene at 10 minutes after 11, and I will leave the Zoom on during this time.
All right, everyone. We'd like to get going. So I'm the moderator for the final session of this seminar series by order or decree from Ron. Thank you. Hey, Ron. We're about to get going. So, can I have the program? We're beginning with.
Yes, and what they're talking about.
Exactly. Was there Laura, right? Starting after coffee, yeah. So, are you ready?
Yeah. Hi, everybody.
Okay.
I'm going to start to share screen.
Yep.
Okay.
Please.
Excuse me.
So Dr. Rosaria Perez hails from Mexico. I believe working with Laura, and I'm very pleased that she'll be presenting our first talk after coffee, oscillometry from the ashes. Don't know what that's going to be. We'll find out. Can you share your screen?
Yeah. Can you see me?
Yeah. Am I sharing this to the?
Yes, you are.
Oh, yes, I am. Very good.
Yeah.
Looks great.
Thank you. Oh, I hear a lot of echo.
Yeah, is it on our end?
I don't know.
If you turn your sound on your computer.
Now it's okay. You hear me right?
Testing? Okay, it's good.
Okay, thank you. Thank you very much and for this space. And my name is Rosaura Benitez Perez, and I'm from Mexico. I'm a pulmonary physician and also a respiratory physiologist, and I work in the National Institute of Respiratory Diseases in Mexico City. The theme that I'm going to present for you is the oscillometry from the ashes, insights on Popocatépetl activity exposure. Popocatépetl is one of the most active volcanoes in our country. 25 million people live within 100. 1 kilometer, 100 kilometers of the crater. After 70 years of inactivity, a gradual increase in the fumarolic activity of the volcano was noted, which started this activity in December 21 of 1994. Since then until now, it has presented a series of eruptions, of which of the most violent was the year of 2000 and the morning of April 18 of 2016. Another explosion was that of February 16 of 2018 after the earthquake that hit Mexico. The last recorded eruption was on May 19, 2023. The expulsion of ash closed the airports of Mexico City for a few hours. The volcanic alert traffic light is a mechanism of the National Civil Protection System that monitors the Popocatépetl volcano 24 hours a day, all year round, to find out its state of activity and detect any anomaly or manifestation that endangers the population. At the left corner of the template, you could see the levels of hazard established by this mechanism. The last eruption in May of this year reached phase 3, yellow, that corresponds to intermediate to high activity, with ashfall in more extended areas. And if we revisit the impact of exposure to volcanic ash, the acute and chronic health effects of the ashes depends of particle size, how much is respirable, the mineralogical composition, these compounds, the crystalline silica content, and the physicochemical properties of the surfaces of the ash particles. Being emphatic about the volcanic plumes that are complex environments of gases of soluble sulfatous and chloride-bearing salts that interact with ash surfaces. All these elements can vary between volcanoes and even between eruptions of the same volcano, making comparisons difficult. The available studies on the health effects of ash volcano exposures date from the Mount St. Helens eruption in 1980. Since then, they have identified mostly reversible short-term respiratory outcomes, acute respiratory symptoms, exacerbation of persistent lung and heart disease, but there are less clear-cut results in long-term effects about lung function. The symptoms suggesting the exacerbations of persistent lung disease have been well described, but most of the studies were carried out before the research development about fine or ultrafine particles, and we have limited number of studies on mortality conducted predominantly in Japan. However, these studies have had insufficient power and other methodological weaknesses to be able to provide compelling evidence of increased risk. In terms of pulmonary functions, all the studies involved evaluated the mechanical properties of spirometry. To my knowledge, there is no study done with oscillometry that you know is a more sensitive tool. We have one previous Mexican study published in 2001 that evaluated symptoms and spirometry from 35 healthy farmers in a community 25 kilometers near the volcano crater during the 1994 Popocatépetl reactivation. They measure symptoms and mechanical properties of the lung a few weeks and 7 months after the eruption. As you can see, the respiratory symptoms diminished, but the baseline spirometric characteristics were pretty normal since the beginning. However, the values became even better 7 months later. So, I previously said there was hazardous volcano activity this year at the Popocatépetl since May, so we decided to look around, and the aims of this study is to describe the lung mechanics and eosinophilic inflammation in subacute post-volcano ashes exposure.
and to describe factors related to oscillometry, including history of comorbidities, respiratory risk factors, or both. Respiratory symptoms, we evaluated for questionnaire during the ASHFAL retrospectively, and 15 days, during 15 days before our visit. It's the intention, the final intention is to do a prospective cohort study, but the results that we will present here, it's a cross-sectional ones. It's the baseline characteristics. And during June 22 and 23, we recruited adults and children who were exposed to volcano ashes to perform pulmonary function tests, oscillometry, spirometry, and pheno at 2 communities surrounding the ashfall area from the Popocatépetl. Here's the map, and here's the crater of the Popocatépetl and signaling. And we visit these 2 communities. The first day, the June 22, we visit Cholula, that is 38 kilometers from the crater, the volcano crater, and also Santiago Jalixintla, that it's 12 kilometers around from the volcano crater, is the most close community from the volcano crater. And this is a beautiful postal that I took from the trip. And the methods that we use, we applied 2 questionnaires, one about history of respiratory comorbidities. We ask people, we ask subjects if somebody, some physician told them about having asthma, COPD, or another comorbidities, and risk factors like biomass exposure, and the time, hours, and per annual hours about biomass exposure, tobacco exposure, symptoms during the ashfall, that it was 1 month before our visit, and during the last 15 days before our visit. We also perform PFT according to ATS ERS current guidelines in the following equipment: spirometry in an NDD, pheno at bedfond, and oscillometry in a tremoflow. And the analysis was done in Stata 17. You could see the descriptive variables and media and standard deviation, or median and percentiles, and comparisons with the student test or human witness, depending of the parametric or non-parametric associations done with person correlation and multiple variable logistic regression. And we have this first table that describes the characteristics of the study population, the baseline, and is a demographic one. About you could see we divide and compare pulmonary healthy subjects and people with a told history of respiratory comorbidities or risk factors. Both groups are very similar, even in the proportion of females. There was more females in both groups. And also you can see in this table the baseline characteristics of the results of the mechanical properties evaluated by spirometry. As you can see, even in the people or the group of told respiratory comorbidities or risk factors, the values of FBC, FB1, and the relation between FBC, FB1 measured by CETA score were perfectly normal, and also the pheno values were, most of them were in the low probability of having eosinophilic inflammation. And you see in this, the final part of the table, the values from the oscillometry obtained from the baseline oscillometry, in the pulmonary healthy group and in the history of respiratory comorbidities or risk factors. Also, all the values, the R5, the resistance values, and the total resistance, the resistance and large airways, the delta resistance given by CETA scores were pretty normal, between the normal ranges. Maybe the only value that it's a little bit above, it's the resonance frequency, but the other values are normal, even between pulmonary healthy and history of respiratory comorbidities or risk factors. And in the comparison, the p-values were non-significant. Also, we did a comparison about, we evaluate the symptoms prevalence related to a history of previous respiratory comorbidities or risk factors. And you can see in both groups during the more intense activity, the phase 3 yellow, and also during the previous 15 days, the symptoms, the proportion of symptoms were very similar between both groups. And also when we compare about the symptoms prevalence related to community distance, one community, if you remember, was 18 kilometers, and another community, I'm sorry, this is 12 kilometers, sorry. This is one error about me, and another is 35 kilometers, and also the both communities have the same proportion of symptoms during the intense phase and the previous 15 days. Even you see the symptoms, the respiratory symptoms that we evaluate, wheezing, chest tightness, sneezing, cough, shortness of breath, and also we ask about eye irritation, were more prevalent during the previous 15 days than in the more intense phase of ash fall. And this is the regression analysis. As you can see, I just highlight the results that we have with statistical significance. And it's very paradoxical. The results were paradoxical because, you know, here we have an association between feeling of chest tightness and the delta given by CETA score for R5 minus R20, the resistance, the delta of the resistance, that is an you know, an indication of small airways, but it's a negative association, and this does not make sense for us. Also, in shortness of breath, we have this negative association between the resistance and the sensation expressed by questionnaire of shortness of breath, and the elastance or the reactance have a positive associations. And also we analyze all this data, including the questionnaire and the question about eye irritation. And it's curious that we found some associations between eye irritation and some parameters of oscillometry. So in conclusions for these preliminary results, these cross-sectional preliminary results of this study, in this cross-sectional analysis, the subjects with reported history or risk factors for a respiratory disease no differ from healthy pulmonary subjects in terms of PFTs and frequency of respiratory symptoms during the acute and post-acute ash fall. Also, the frequency of respiratory symptoms was similar in the communities independent of the radio of the volcano crater. The basal values of PFTs in the evaluated subjects were between the population normal range according to CT score, including oscillometry. We found negative and paradoxical associations between chest tightness and the delta, the CT scores of delta resistance and shortness of breath, the delta resistance, and also the index, the complex index of delta resistance between R5 or the total resistance that measures or is a proportion about the resistance of the really small airways, and also between elastance and resonance of frequency of resonance. Yeah, and also we found associations between some respiratory function variables and eye symptoms. So we have the strength that is in our community, the first study with oscillometric values, but also we have weaknesses and opportunity areas that we don't have the geological and meteorological analysis today. We will have it in the future, but for the purposes of this presentation, unfortunately, we don't have about the content of the composition of the ashes that fall in this eruption, this last eruption, and also this analysis was cross-sectional, but the intention is to return to this community and also measure again all these variables and in order to do a cohort and prospective study. And also one of the weaknesses is the people and the subjects that we questioned about the respiratory risk factors and comorbidities. They maybe weren't too ill. You know, they were very healthy in terms of pulmonary function. So it's difficult to extrapolate the results of, they have the same, values of PFTs, and also the symptoms were no different from the no comorbidity group. So maybe in the future, because the Popocatépetl volcano could be, it will be continue erupting. So maybe in the future it could be available to just recruit people with real identified respiratory comorbidities. So thank you very much. And this is pictures from part of our work team. So thank you very much. If you have any questions, you could ask to Dr. Laura Gochkoa.
Very good. All right. The first question I see is Ron.
Yeah, so
Thank you very much.
amazing field work, and we're going to drag Chung Wei into this debate too, because she's also been dragging an oscillometry out to ash exposed people. But before we get to that, I would take issue with you when you were calling some of your results normal. Did you not show in the slide before table 2 resonance frequencies of 24 hertz?
Yes.
And didn't you have 1.8 kilopascals per liter on AX values, which would translate roughly into 18 hexapascals or 18 almost centimeters of water per liter? And I would say that those in my practice I would consider abnormal.
Yeah.
So am I misremembering the slide, or do we have a different way of interpreting oscillometry results?
Yeah, I couldn't hear you very clearly. It's just a little far from the microphone, but I think you are talking about
I thought you showed abnormal AX values when you were calling them normal. And I
Yeah,
thought you showed a resonance frequency at 24, which definitely is abnormal.
yeah, yeah. Yeah, thank you very much for the comment. Yeah. I don't know if you have to say something, Dr. Laura.
Okay, Laura, unmute yourself. You're on the spot.
Oh, thank you. No, well, one of the problems that we are having is that these we apply our reference values to these people, but our reference values comes from the iOS, from Bayer. We try to find in all those ages a reference equations made with the same device, with the TremorFlow, but we didn't. So we try to apply the ones from Dr. Usben, but I think that the ones from 2013 are also a mix that include the iOS. So probably that could be another problem. So, well, right now we are recruiting healthy people from all ages using this other device. So perhaps when we reanalyze the data, we will find a better answer, because as you can see, the C-score in when we apply our formula, it's almost normal. That's why we were thinking in these results.
Yeah, that's one of the reasons why I like looking at absolutes, because we always have this conundrum with our reference equation appropriate to our population. So you're definitely showing an AX, which in centimeters of water, certainly in hexapascals per liter, would be 18 and 19, which I think clearly would be not normal.
Yep. And
your resonance frequency at 25 and 25, also I have a hard time calling that normal. So I would consider those positive findings. I don't know how other people in the audience feel.
Is it possible that the subject population they're smaller in stature and height, so that those are actually more closer to normal? Why they're predicted?
Even if they were 5'0", 5'2", they would achieve those numbers?
No.
I don't think so.
Yeah.
Jeff.
Chungwei, what is your AX?
I know it's pretty normal, so
You-
Joyce probably knows what my AX is.
Oh,
Yeah, probably.
Yeah.
So
Yeah.
I would say no, it's not a height issue.
Yeah, we
Rosa, thank you very much.
Can I ask you to stop sharing your screen just in case we get
yeah.
That's fine.
people?
No, I think the issue with reference data is always there. I think for now, the data that came from Eli Ostrin and her group in 2013 is the best. And the reason for that is that it was very well controlled. If you read the methodology in that paper, it is very well controlled, and they had standards for, comparing the devices outside of patients. They transported around calibration tools and stuff between the labs and so on. And it's not only iOS, they also had a home-built device and had another third device. I don't remember the identity of it. It's probably not perfect, but if you go back to the study that Ron Andron and other Sultan was involved in, the comparison studies between devices, just absolute values, it turns out that most devices are actually in what would be perceived as being a normal or low test load situations. Almost all devices are very similar. So if you compare with what you expect to be normal, which would be probably around 0.2, 0.3, something like that for resistance, and lower single digit or 0.1 to 0.5 in AX, I don't think that they will be very different from device to device. So I'm not super worried. I'm not super happy either. And of course, there is work going on collecting reference data, for example, within the GLI initiative. So it will be better, but I totally agree
what
with.
Charlie presented yesterday was actually very illustrative, but where it actually does make a huge difference.
No,
I mean, out of thousands of patients, you had maybe 100 that were reclassified when you're using Ken Berger's versus Zoli's normal data.
Yeah.
What's the altitude of the study site?
2000.
2016?
No, yeah, it's like
2,000 feet. Okay.
2000 and yeah, an average 2,000, 200
No,
meters.
It's not high enough. No. Could be a problem.
But
In terms of the negative association of that, I don't think any of us here have a clue what's going on there.
Yeah, well, an interesting thing is these are healthy. They started out with very healthy parameters and they have symptoms of irritation. So is it necessary that in healthy people, irritation causes poor mechanics? Healthy people have a lot of room, wiggle room to adjust their mechanics
depends
based
on
on
where
how
they're
they're
being-
feeling.
But it depends on where they're being irritated. So how would you link, what's the mechanism that would link eye irritation, something's on the lung? I mean, we really don't understand reflex innervation along all that well. Most of it was done back in the 60s. I mean, we've shown that AX is related to anxiety. Now, why would that be? I mean, I'm anxious because my AX is wrong. I mean, but that doesn't mean there isn't. That doesn't mean there isn't. I just think that, the physiologic plausibility of it becomes difficult. And then there's a statistical problem here, I think, and that is you've done so many correlations, you would expect to see a certain number of positive ones just by chance unless you control carefully for that.
Yeah.
And my statistics aren't that strong, but I know that even the Bonferronis that we saw yesterday, that's not a particularly conservative correction, and there are other ones that would be more conservative.
I agree with you. The risk for a false positive. Or
Well, no,
whatever.
you do the math.
Yeah.
How many associations? do you-
1 in every 20 would
Yeah,
come out.
you'd expect five out of 100.
Exactly.
Well, if the issue is that we don't understand what irritation does in healthy people, I wish you luck in future volcano eruptions and you can measure unhealthy people.
Well, and then what's the
Does anyone get my joke? Anyway.
What's the particle size of the ash? I mean, I remember visiting Denver right after St. Helens, and the ash was really big chunks. But did you characterize the particles at all?
There were particle collections done. I was actually there the first day, so I saw it being done.
Yeah. But the results of this analysis of the particle size and also the composition of the particles, the silica percentage or something like that. The analysis is not done yet, so we couldn't present this. We have the previous work of the 2001 published, and then they say that at that point the percentage of silica was the minimal, was 15% in the ashes or something like that, and the particle size was also is not the very the respirable factor was so significant, but we don't know if this eruption was the same. The eruptions aren't the same always.
Well, we did a study in Colorado at high altitude and hard rock miners, where the major in molybdenum mines, mostly it's silica. And to see an effect on lung function, you had to be right at the face of the crusher where you had huge burn for years. So I you're an occupational person, still. What do you think?
I think, I mean, definitely the dose and the exposure,
Yeah,
we can bring up that kind of effect. I'm just wondering, you know, if it's also some of the sample. I think it just gives me pause, and I would want to kind of follow these people over time. We don't know where they started.
Right.
And so that's the hard part, you know, and I think we see that in miners and these military deployers all the time, you know, and yeah. That being said, the mine that you're talking about, the Henderson mine, has better controls than many others. So we have seen
Well, ours was mostly at Leadville, that was at the summit.
the Climax mine, right?
Climax.
Yeah. But some of the others, even within a year, we've seen like decrements in FEV1, and it's that serial part. So I think this is one of those things, like in like critical care, we always talk about like a CVP is not helpful, just, you know, but the dynamic assessment, you know.
Actually, now that I think about it, what about cigarette smoking? Did you control for that? How many of the folks were smokers?
Yeah, we control on the last table. The regression analysis was controlled for these co-founders, and also in all the population, only one the participant was a tobacco index above 10. The another participants, we have in total 5 participants that active tobacco, but the tobacco index was less than 10 tobacco pack per year.
Yeah, we showed that there was a profound difference between people that were exposed to hard rock who did or did not smoke. The physiology of those two groups is profoundly different. And so making sure that you understand the smoking part of this is important.
So I think we should move on, but one more question from Ramon, I see.
Thank you. I presume that this was a field study, that the measurements were not carried out in a lab lung function, right? Okay, so my question is, if you standardized the posture of the patient and also the relaxation, because if the patient is subjecting the device and the posture is not very good, and there is a bit of contraction of the abdominal muscles, I don't know. I know that it's very difficult to control the patient posture and attitude in the field studies. It's more easy to standardize within the lung function lab. So could it be possible that there was a bad posture or some kind of contraction to subject the device or something like that to explain these relatively low values of reactants?
Yeah, it could be because we are very well. The people, the participants, we are on the field doing the studies. The pulmonary function tests were just like 4 people, and there was like you know, a lot of people waiting for the test, and yeah, it's difficult. It was difficult to get order to give us some you know, the number 1, 2, 3, like a folio or something for the people. So yeah, it could be, but you know, we don't have any measurement about maybe this particular person or the particular subject could has bad posture or something. We didn't measure that, so it could be an explanation, yes, but we can't adjust for these factors because we didn't measure.
Thank you.
Can I make just one more?
Very quick.
Oh yeah, sorry. I was just going to say that I know this is hard to do out in the field, but I also wondered just the nature of the exposure. If in the future you could add on DLCO assessment, just because it's assessing something kind of different with that particulate matter. That's one other thing to kind of add to the monitoring. Not to make things way too complicated.
Yeah, that's a fantastic idea, and yeah, in the future we want to do everything, like move at some kind of a pulmonary function test. If we could move cardiopulmonary function for another, that will be great. Maybe in the future, maybe.
The miners outreach clinic that we do, the NDD Spiro DLCO is fairly portable, and we take it to rural location. So NDD has a good device for that.
Okay. Well, let's thank you again for an excellent talk. And I have the pleasure of introducing Zoltan Hantov, Zoli, as we know him well, who needs no introduction, really. He's going to speak to us about interbreath spectral oscillometry, strengths and limitations. Zoli, can you share your screen?
Yes, thank you.
We see your desktop.
I get rid of my second monitor and hope that you will see my presentation. I have to try to share the screen.
There it is.
Oh, good.
You can go into presenter mode, maybe. Wonderful.
I just don't see my own screen, but it's okay.
Take it away.
Sorry. Oh, thank you very much. I hope that my talk won't be less innocuous than the ashes were. I put a cut pedal. So thank you very much for this opportunity. This topic has been touched since last year quite thoroughly. So first of all, I thank for my co-authors. First of all, Gergő, who developed absolutely amazing software to this multi-frequency interbreath tracking. And in addition to my Hungarian colleagues, I'm very indebted to Joyce and Changwai and Ron to share all these data with me, enabling to compose small, relatively homogeneous groups of subjects to compare. I have some conflicts, but not terribly bad. So the backgrounds. It has been long documented that respiratory impedance vary with lung volume. These were not systematic studies, but clearly indicated that at different phases of the lung volume, we have different impedance spectra. Approximately in the same time interval, quite a lot of attention was paid on the sinusoidal oscillations following the interbreath changes. And this was the area of conflict when we all fell in love with the frequency dependence of impedance and neglected that among these impedance data, there is a lot of nonlinearities, and we were stubbornly following the linear system analysis, and we are still using that. I think the breakthrough with the current oscillometry and the interbreath changes, that time called within breath, was in approximately 20 years ago with the Delacre study, which was a great physiological study aiming at expiratory flow limitation. And since then, a couple of studies appeared, starting from acute exacerbation of COPD, infants, preschoolers, asthmatic children, adults, and so on. In the background, we have a study in which we compared the 10 Hz oscillometry interpret loops data with extracts from composite signals at 11 Hz. And apart from the fact that the 10 Hz data are much consistent, much smoother than the 11 Hz proxies, the correspondence between the 10 Hz end expiratory resistance and 11 Hz expiratory end expiratory resistance, inspiratory and inspiratory resistances, and basically all the resistance values. And quite surprisingly, the reactance values were quite consistent, although we expected that at 11 Hz, reactance should be higher fractionally than at 10 Hz. Anyway, we set the following games in the study. We wondered if we derive interpret impedance data at different frequencies in addition to the 11 Hz, what would we find? But we wanted to see whether the looping patterns and derived interpret measures are consistent across the frequency range, or we can find some changes indicating probably different origins of the mechanisms in the central and the peripheral parts of the lungs. It was inevitable to address the question of the oscillometry signal, whether it is appropriate for this multi-frequency tracking. And finally, but not least importantly, we revisited the upper airway wall shunting, which is buried as an issue deep, and nobody wants to talk about that, although it was a really solid finding a few decades ago. So what we included in the study, tremor flow measurement, the C100 oscillometer measurements from Toronto and Montreal, healthy adult subjects, the patients with ILD, with asthma and COPD were randomly included in these the comparison. And the comparative analysis was made with a custom-made software, which is a National Instruments-based LabVIEW program. It's Gerger's extremely useful tool. Just to look at the patient demographics and the force spirometry data, not going into details. There are differences which are either expected or not expected, but it is not very relevant. This is the surface which we see in the software. So lots of tables listing and expiratory and inspiratory values, minimum and maximum values in resistance, reactance, with mean, median, and SD, and whatever else. Probably most importantly, these graphs give you an idea how the end expiratory resistance changes with frequency. This is the black one, and inspiratory is the red one. The mean value, which is an average, the conventional spectrum in oscillometry, is the yellow, very, very close to the end expiratory value in this example. And we have maximum resistance points and minimum resistance points, and the end expiratory minus minus end inspiratory resistance, which is also changing its frequency. The same for reactance here, and also the loop areas are listed here. So what we see at the first sight in a three-dimensional arrangement of frequency versus resistance versus volume or versus flow loops, the same for reactance here. And we can see all the frequency components here, quite a messy plot. So if we remove these friendly neighbors, like the 13 Hertz, from the vicinity of 11 and the 19 from the 17, etc., we have a nicer picture and better to follow up. So if we pick up the individual instantaneous impedance data from these groups, these are the median values. The end expiratory value is the pink here, covered by the mean value. This is the healthy group. The end inspiratory is somewhat lower, and the minimum is even lower, and the maximum is much higher than the normal tidal and tidal change values. And similarly, we have the highest value for the maximum X and the minimum X. They are not coinciding with each other. They are different estimates. So the ILD subjects have a higher, wider range. The asthmatics cover an even wider, and the COPDs, who are relatively homogeneous in contrast to the asthma group, they have enormously high instantaneous maximum resistance and instantaneous minimum reactance in the breathing cycle. If you plot, or if you just concentrate on the end expiratory and end inspiratory values of resistance and reactance, we can see that basically lower values are found at end inspiration in resistance. It's more marked to see how the reactance at end inspiration converges among the groups. So the initial end expiratory span is much reduced at end inspiration, as if every subject gets normal when completing the tidal inspiration. Of special interest is the delta R and the delta X. That is the difference between the end expiratory and the end inspiratory resistance, how it changes with frequency. We can see that the healthy persons and the ILDs are very close to each other, and they basically have a frequency independent difference in the tidal change in resistance. In contrast, in the asthmatics, we have a gradual decrease, and most strikingly, the highest values found at 5 Hertz, the COPDs, gradually lose this difference, and at the upper half of the frequency range, there is no tidal change in resistance. I mean, between the end expiration and inspiration. This is very striking. The same thing with the delta X shows at low frequencies that the normals and the ILDs have lower reactance values at end inspiration. That is why delta X is positive, but this difference is gradually lost and gets slightly negative at higher frequencies. It appears that the very inhomogeneous with great scatter asthmatic group is shifted just below, whereas the COPD delta X tendency is just the opposite to the others. Of course, we can derive conventional measures from the spectra. So the different reactance phases, we have gradually higher resonance frequency at end expiration, and this difference is diminishing at end inspiration. On the right hand side, the something average value, probably not to have. We don't have to look at it. AX also displays a different, a similar trend. Huge differences between the low AX normals and ILDs, the medium but very scattering asthmatics, and the COPDs. Now, we were curious about how the upper airway shunt might influence these intrabreath frequency dependencies. So I refer to quite a bunch of very significant work from the Nancy group in the 80s and 90s, who pointed out that the upper airway wall exerts a significant shunt effect on the distal respiratory impedance, even if the cheeks are firmly supported. So we just created an average value from 5 cooperative subjects in the lab doing Valsalva maneuvers with not enormously closing the, or contracting the neck muscles. So we find that the five persons have quite different inter-subject differences in reactance and probably less in resistance, and also the inter-subject variabilities are high. Anyway, we averaged all these data with the assumption that this is a small but maybe representative average for an upper airway shunt impedance, which is not true, and which might be absolutely ridiculous because. Sorry?
Carry on, Zoli.
Okay. So we first made a.
Oh, yeah. God, yeah.
Somebody out there in the Zoom world, please cut your microphone. Thank you.
Thank you. So this is the first simple attempt to compensate for the upper airway shunt impedance, which was introduced by Michael Zons and colleagues long time ago. And this was simply a parallel removal of this shunt impedance to get the subglottal impedance. The other compensation was proposed by Kohlbergs and Van der Woestijnen a little bit later, who realized that this shunt impedance is not lumped. It is maybe distributed along the supraglottal pathway. So they imposed a tube impedance and shared these lumped shunt into one in front of the tube and one distal for the tube. And these compensations or corrections are different. I will show you only the second one because this is sometimes overcompensating. But this is a very rough assessment, the differences between the uncorrected and corrected spectra. Most obvious is that the frequency dependence of reactance is more straight, not ceasing that much as in the uncorrected spectra. The other thing is the wider scale covered in the correction with the assumptions that these are representative upper airway impedance, which is of course not true. So nobody has in this 160 patients upper airway impedance measured. So we can't make this. It is absolutely impractical. It is just in laboratory circumstances when it matters. So then, just looking at the delta R and delta X in the uncorrected, which we have seen minutes ago, and after correction, same scale. So now we see that basically the healthy and ILD subjects, delta R is the same, maybe fractionally higher. But the sharp decrease in delta R in the asthmatics changed into a more flat, frequency independent pattern. And now the COPDs don't approach zero at higher frequencies. They converge to the asthmatic group. And there is not such a radical difference between the uncorrected and corrected the delta X data. Probably the correction brings the COPD curve down and has which departs at a high frequencies from the asthmatics, and the asthmatics basically they stay where they were, but the normals and the ILDs are now basically above zero at all frequencies. So it does matter whether we have an assumption that there is no shunt effect at the entrance of the respiratory system. So we can conclude that technically we can follow the intrabed changes at multiple frequencies, which are simultaneously measured. We can demonstrate that the spectra and the derived measures from the spectra, like the resonance frequency or AX or R5 minus 19 and things like that, they have a wide, exhibit a wide change during the breathing period. However, it is clear that the lowest frequency, that is 5 Hertz, impedance data have large scatter, and they provide us with a quite poor temporal resolution, so not hitting the zero flow points and things like that. In addition, these C100 and the earlier Resmol spectra are probably not very optimal because there are close frequency components next to each other primes, which are fundamentally useless. They don't contribute to anything in the spectral evaluation, but they interfere with each other and limit the range of the intrabreath modulation of ZRs, because we have to band pass the 11 Hertz and the 13 Hertz and all the others uniformly with the plus minus 1 Hertz range to keep off the biasing effects of the neighbor. And this limits the modulations, the side loops, which carry the intrabreath information. Anyway, so we were quite happy to see that at the end inspiration, impedance data, impedance spectra sort of converge from the different disease groups. They are more similar, far more similar to each other than they were at end expiration. And it was surprising that the conventional average impedance data are the closest to the end expiratory spectra in all the 4 groups. Now we see with reservations that the preservation of the intrabreath looping patterns and the intrabreath indices across frequencies are quite variable, and this may indicate that the loci of the tidal mechanical changes are different. So in the last delta R comparison with the upper airway correction, we can see that probably there is a central airway dilatation which is reflected in the delta R, which is contributed quite a lot at low frequencies in the obstructive patterns, indicating that the improving homogeneity of the peripheries also add to the decrease of the delta R. So these delta R and delta X patterns are probably will be very good as functions of frequency to characterize the respiratory diseases more more in detail than the average impedance data can do. So we have shown that however primitive this simulation or the correction was, because they were not original data for the opera wave impedance, but they do influence the interbred dynamics. So the task is clear and almost finished by now, that optimizing, that is pruning the pseudo-random signal spectra will give us the possibility of having less contamination from the neighboring frequencies, plus the option that we can band pass with a wider range and include the interbred modulation side lobes for tracking the interbred changes more faithfully. Thank you very much for your attention.
Thank you, Zoli. All right, I see a hand right up from Jason. Go ahead, Jason.
Yeah, hi, Zoli. Thanks a lot for that talk. Very interesting stuff. And it's great to see that you're maximizing the extraction of information intra-breath as well as averaging. I think there's, I think many have realized there's a lot of information there that's just being discarded, and it's great to see that you're figuring out how to get it. I think you mentioned mostly about the things that would affect intra-breath resistance, and you can imagine that would be changes in airway caliber and maybe flow and so forth. One thing I've wondered about is if you have someone spontaneously breathing, then as they inspire, they activate the respiratory muscles and then they turn them off during expiration. And I would have thought that would have changed the stiffness of the chest wall. And since you are measuring respiratory system elastance, I wonder if you see any evidence of that you could interpret.
Absolutely, Jason. This is a very, very good point. So in normals and in most of the ILDs, but no, just to speak about normals, we assume that these quiet tidal breathing is moving on the dynamic or the quantitative PV curve, a linear portion. So there is no flattening or over distension of the lungs. What is the difference? In inspiration, we have activated inspiratory muscles, whereas in expiration, we don't need to activate the expiratory ones. So that means that the stretching or the activity of the chest wall generator, its internal impedance, when the muscles are active, it's increasing and it's adding to the reactance. That's why reactance goes down with inspiration in healthy persons. And maybe on top of this, in ILD, the restrictive pattern, the fibers and still homogeneous lungs also get into some tension, some stretching, and that brings the end inspiratory position down. Now, we can say that in obstruction, this should be the same with inspiration, but in asthmatics and in COPD, reactance goes up with inspiration, which has, for me, just one logical explanation. I can't figure out more than that. There is an increasing homogeneity with inspiration, which means that the same lung with more homogeneous peripheral units will result in a higher reactance. it's a higher compliance. And this is more than offsets the contraction of the inspiratory muscles.
I see. Very interesting. Yeah, makes sense.
Yeah, I'd like to actually add to Jason's comment. It was actually apparent, I think, in Chung-Wei Chow's paper comparing, and your paper, and I think it was Joyce Wu's first author, that compared ILD loops, looking at reactance loops, and the slope of the loop of the ILD patients was, I think, positive, if it was volume, I believe. Whereas in COPD, it was negative. And it seemed to be, ILD has always been an interesting or challenging disease for oscillometry to basically separate from healthy populations. And it was looking like there was a hint that the interbreath oscillometry, by looking at this difference between COPD and ILD, and maybe ILD in health, but I wasn't sure about that difference. I can't remember it. That was perhaps a potential index that could be used. If you're suspicious of a patient who has on their x-ray some diffuse interstitial disease, but maybe emphysema, you can actually look at the function and you'll have a negative slope for COPD, but a positive slope on the interbreath versus volume loop for ILD. But that was me just dreaming. I'm not sure if that's the truth. So I wonder if you have any comments on that, Zoli.
That's really a very nice dream. I am having this. I'm recurrently having the same. All the more that in this study we excluded the fibrinolytic plus emphysematous patients. So this was clear ILD, but still there are quite a lot of expiratory flow limitation patients in this population. There is a very homogeneous, probably 1/3 of the ILD patients which we have analyzed so far, which is supernormal, super stiff, and super homogeneous. And then another 1/3 who are just overlapping with the normals. And the third third is where something is wrong with the homogeneity, and expiration can get into expiratory flow limitation and things like that. So it is very, very interesting.
Right.
Well, that's because ILD is typically mixed. It's got to have a major airway component, and you can see things being offset. Zoli, I think you explained it, but I'm still struggling with it. The one thing that struck me with what you're doing is the difference in patients with COPD down at 5 Hertz when there's a marked increase in reactance, if I remember that correctly. What's your explanation for the frequency dependency of reactance in COPD again?
Well, actually measuring making measurements in the frequency range, where the basically high compliance, high dynamic compliance. This disappears because gradually the spatial heterogeneity dominates and pushes down reactance and elastance, and it stays down by the lowest frequency, which we measure during spontaneous breathing. That's 5 Hertz or something like that, and it is not going to catch up with the normals any longer. But there is a crossing point. If we had measured probably from 0.5 Hertz, which is impossible during spontaneous breathing, COPDs, we must have revealed a high compliance, which gradually falls. That is, reactance doesn't go up that fast, but stays elongated below zero. That's probably an explanation.
So what kind of COPD patient? I mean, COPD is sort of a garbage term that's related to all sorts of. It usually refers to somebody with airflow limitations, smoke.
I take exception to your mind.
That's what I was hoping I.
So they all meet the gold criteria except for the pre-COPD. But the ones included here are all gold criteria.
No, that just means the FEC over.
Yeah, so they
FEV1
have
over
they have
FEC.
airflow obstruction and they have a smoking history. And there are heterogeneity of patients who have varying degrees of emphysema.
Well,
Our imaging friends are in a good position. Their job is secure. We need them to figure out what's
Well, that's
going
what I
on.
was going to ask. What's the diffusing capacity in this group, and what is the emphysema score and CT in this group?
So there's heterogeneous. Some of the emphysema score will be within the normal range of my practice, extremely well below 6% of COPD. I call it 10% of my practice. I've got others in that group going up to probably 35 on the LEA.
Right.
We have fusing capacities that have, again, the spectrum of relatively perturbated to quite badly reduced.
So one thing you might want to consider is progressing the interbreath observations against how much emphysema you actually have.
This is where we're having fun as we speak.
Oh, right.
It's not ready for prime time.
Okay. Thank you. Thank you, Zal.
Oh, Bela is up, and then maybe we'll go to Leonard, and that'll be it. And we'll move on after that. So Bela, go ahead. Oh, we can't hear you. You're muted, Bela.
Yeah, so very nice talk and really beautiful, clean data. I think I have one comment and a quick question. One is that basically, I think that some sort of a structural modeling is really due. That could help understand all these complex data. You know, all how the different impedance parameters depend on lung volume and or flow and so forth. So that's my comment. And the question is that if you take one of the higher frequencies, like 20 hertz or above, you probably have enough cycles per breath to follow the time variation of impedance. And I wonder what kind of fluctuations do you see there? Like, I assume that if there was like a major airway closure or opening during the breath cycle, this might show up in that resistance.
Yes, it really does. So the problem with the 5 hertz and neighborhood interbreath is even if we don't need overlapping or more cycles to include in the instantaneous spectra, it is still very poor temporal resolution, and this resolution improves with higher frequencies. So that was really one of the aims which we wanted to look if we find the patterns of interbreath changes are consistent at higher frequencies, then the better temporal resolution would pick up these changes in an improved manner. So it is still open, but it's a very good point. Your comment is very well taken. So we have actually started with constructing relatively elaborate model with just a couple of generations, not anatomically faithful, but maybe large airways, medium, smaller, very small, and upper airways, a lot of upper airway segments with flow and volume dependent nonlinearities to simulate loops, which will, if we turn the simulation model, the different potentiometers, and realize that, wow, we have seen that in a lung transplant patient, and we were not realizing what the mechanism was behind. So that would be great. It is probably a couple of months from now then we finish this simulation model and start the school hours with turning the potentiometers and imitating or trying to find the real world interrupt loops. Thank you, Bela.
Yeah, looking forward to that modeling. Leonard.
Thank you, Solly. Maybe this is part of my ignorance because I don't really remember the cover paper, but when you do the correction, well, first of all, how necessary do you think it really is in daily life? I mean, would it really make a huge change if one were to implement that? Secondly, how individually does it need to be connected? I mean, can you have somebody with a really small body size use the same correction factors as compared with somebody who's much bigger, or how does it apply?
Well, if I were connected to facial surgery people, I would probably be able to map what was the structural background of the differences are. I think it is not very feasible. So the Nancy group made enormous effort to implement head generator canopies and things like that, but the routine oscillometry is not practical, so we can't follow that. And there's really, if I compare these 5 persons whose upper airway impedance we measured, there is not macroscopic correspondence between the impedance values and the look of the size of the head. So it is probably it remains an unsolvable problem, but we should be aware of the fact, and we should probably never display equipment with subjects without cheek support.
Exactly.
Where did I hear that before? Okay, well, thank you again, Loli. We'll move on to the next speaker. No, not here. Are you in here? So while she is loading up the spot, I'm pleased to introduce Chun-Wei Chow, University of Toronto, head of the transplant group there, and you can see her title right there. If you're ready.
Well,
take it away.
am I sharing? Just. No.
No, I think the parents
Okay. So thank you very much for these 2 wonderful days. And really, my only disclosure, really, my truest disclosure, is that I'm addicted to oscillometry, and so 3 years between a hit of oscillometry is hard to take, and I will look forward to next year's symposium. But I also want to say that it's been incredible having these conversations. But my dream actually next year is that we will get many of our physiologists here in-house and have these conversations over beer. So what Ron had asked me to do was actually to give an overview of the role of oscillometry in lung function monitoring after lung transplant. And I know that many of you are not lung transplant respirologists, and so I thought what I would do is just very quickly go over the current standard of care of lung transplant patients and review with you some of the oscillometry studies that has been done in this particular population, and then at the end, really go over some of the future work that can be done. And in the field of lung transplantation, it is FEV1, not so much spirometry, but really the FEV1 that actually plays a major role in terms of the primary metric of graft function after lung transplantation. And within the first 3 months post-transplant, patients are actually measured on a frequent basis. They do home spirometry on a daily basis, and at least once a week in a lab setting. And specifically what we're screening for is evidence, any indication that there is any evidence of acute rejection or infection, because that is a time period when acute rejection and infection occurs. And then after the first 3 months, the lung function monitor continues to be the FEV1, but here the major focus is on trying to maximize the FEV1 to get the best lung function that is achievable post-lung transplant, because this actually has a great deal of implications in terms of the prognosis. Patients who do not achieve a baseline FEV1 of more than 80% predicted have a much higher death rate, and survival is significantly worse, with most patients achieving the maximum lung function or a maximum FEV1 at anywhere between 12 to 18 months post-transplant. And lastly, FEV1 plays an important role in the definition of CLAD, chronic lung allograft dysfunction. And chronic lung allograft dysfunction is really the major impediment to survival beyond 2 years post-transplant. And it plays a significant role because 50% of all lung transplant patients will develop CLAD by year 5 post-transplant. And as time goes on, that incidence increases over time. But there are clearly some huge problems with using FEV1 as a primary metric for monitoring a patient's lung transplant. There have been quite a number of studies that have shown that FEV1 is actually just as good as a flip of a coin in terms of being able to detect acute rejection. And yet many, in fact, most lung transplant centers around the world do not do surveillance bronchoscopy, and they only bronch when they see a drop of 10% or more in the FEV1. So that's problem number one. Problem number two is that when you're trying to sort of figure out, what is a patient's prognosis based on their baseline lung function, the problem is that you don't actually know what the best baseline FEV1 is until it plateaus and drops. So it's really a diagnosis of actually a retrospective diagnosis, and you just keep hoping that that lung function will increase over time. Now, the other problem with using the FEV1 in the definition of CLAD is that the definition of CLAD is that it has to drop 80 to 20% from the baseline value, but you have to wait 3 months before you can actually confirm the diagnosis. And so if you're a drug company and you've got a new therapy that you think would be actually helpful in terms of treatment of CLAD, you're really shooting yourself in the foot, because the diagnosis is such that by the time that diagnosis is made and that you can start your therapy, is that lung injury is already very much fixed, and it may not be reversible. And so this is sort of where my group came in, and really came with a very, very simple hypothesis, which is that graft injury of any cause is reflected by changes in lung mechanics. And in this audience, you know that oscillometry is really good at being able to detect changes in lung mechanics. And so the corollary is that oscillometry can detect graft injury of any cause much more sensitively than spirometry. And so it was our job in terms of research studies to show that oscillometry can actually be useful in terms of evaluating clinically relevant outcomes. And the first study that we did was really looking at the role of oscillometry in the detection of acute rejection. And what we used was actually a gold standard diagnosis of rejection, which is a biopsy evidence of grade 2 or higher rejection. And grade 2 or higher rejections are rejections where we will actually treat with increase in immunosuppression. And what we were able to show is that when we actually follow these patients. And so what we did was every patient who had a double lung transplant were enrolled prospectively to have oscillometry before every single spirometry measurement that was done in the lab. And what we were able to show was that in these patients who actually had grade 2 or higher rejection within the first 3 months post-transplant, was that the AX and the R5 to 19 values were significantly higher than that of patients who had biopsy evidence of no rejection, and that after treatment, that these values actually improved both in terms of the AX and the R5 to 19. Now, what didn't actually get into the paper, because it wasn't clinically statistically significant, was that patients who had a lower grade rejection, A1 rejection, actually had these intermediary values that was consistently observed as we follow patients over time. And so this then led to sort of a refined hypothesis, which is that the changes in the oscillometry values of an individual over time, so these little bobbing up and down of the AX or other metrics, was actually a marker of lung injury, and that this would be associated with clinically significant outcomes. And what we did was that we calculated the within subject variance, which was a mathematical calculation of the variance over the measurements of these values over 1 year. And in this paper, which was done by 2 very talented graduate students, we really want to answer 2 questions. Number one is the variance of oscillometry measurements over the first year post-transplant associated with the burden of acute rejection within that 1 year? The second question that we wanted to ask was, is the variance of oscillometry within the first year associated with an increased risk of subsequent CLAD? And in order to normalize the burden of acute rejection, what we did was, in our protocol, patients underwent surveillance bronchoscopy at very defined time points over that first year. And so we added the sum of all the A grades from 0 to 4 of all their transbronchial biopsies over the 1 year, and then divided it by the total number of biopsies, where we were able to provide a numeric grade. And this is our study population. As I mentioned, we basically enrolled everyone who agreed after lung transplant. We stopped, there was a somewhat catastrophic event that happened in March 2020. And we were able to, within this population, study 230 odd patients who had at least a year of follow-up and who had oscillometry measurements done at least for the first 3 months post-transplant. And the study population is very much reflective of the current cohort of people who undergo lung transplant, slightly middle-aged, a little bit more men than women, and mostly for ILD. And what we were able to show, indeed, was that the variance of X5, AX, R5 to 19 during the first years post-transplant was actually associated with the burden of acute rejection during that first year. And importantly, what we were able to show was that the FEV1 was not. And we had shown in the first paper that FEV1 was totally insensitive to acute rejection. So this is really confirmed this result. And so here are the sort of p-values there. Now, the next question that we wanted to ask was that, can the variance in oscillometry predict subsequent CLAD? And here the patients had to be followed for at least a year. What we did was we actually had a time match the patients who actually had CLAD at the time of CLAD onset to patients who remained CLAD free within that time frame in terms of duration of follow-up. And what we were able to show in this was that indeed the variance, and specifically the variance in X5, was very much associated with the subsequent development of CLAD. And we had a total of 28 patients at the time of when these analyses were done, and they were time matched to 129 patients who remained CLAD free overall. Now, what was interesting was, of course, that the ACE score, the burden of acute rejection, which is the highest, acute rejection is the highest risk factor for subsequent development of CLAD, was that this was not associated at all with the development of CLAD. And perhaps it's not really surprising because the ACE score was calculated periodically, and it's very much based on the detection of acute rejection in biopsies. But biopsies are random sampling in only a couple of regions of the lung, and that it also did not capture all the other insults to the graft during that first year. But by contrast, oscillometry was done very frequently during that first year, and it was also detecting things that the biopsies were not detecting. So, so what we really concluded from this study is that, in fact, oscillometry is very much a marker of lung injury in the lung transplant population, and that this is a personal belief of mine, but that oscillometry really should be added to the standard of care in the monitoring of patient after lung transplant. And if we were able to actually identify and define patients who actually developed that at the time that they had this initial drop in 20% in the FEV1, then this may actually allow us to actually, look at CLAD and, and if we're thinking about therapeutic interventions, is to do so before the horse has left the barn. And so I'm just going to end here and thank my funding agencies, and to thank actually my many mentors in oscillometry, including Zoli, Charlie, who explained to me what the imaginary portion of breathing was all about, and for Ron for getting me addicted to this field. So thank you very much.
Well, thank you, Chun Wei. I think you can take your own questions.
A response from a typical man. What's the pathology of CLAD? I mean, what's it under the microscope when these people crash? What does that look like?
Well, there are two pathologies, and the most common one is a bronchiolitis obliterans, which is really the obliteration of the small airway lumen with connective tissue. And that one has a significantly better prognosis. It is the most common form of CLAD, and the prognosis there is once you're diagnosed, the survival is anywhere between 2 to 4 years. The less common form of CLAD is a form called RAS, restrictive allograft syndrome, and it is primarily an upper lobe fibroelastosis. And in many respects, it is almost in both in terms of physiology and presentation, almost like idiopathic pulmonary fibrosis, because once that diagnosis is established, survival is between 6 months to a year. And what we're beginning to learn now is that people who have BOS can transition into a mixed phenotype and sort of progress into a BOS RAS picture. And once that transition occurs, the prognosis also significantly worsens.
So that raises a couple of questions on observation. One, the observation would be that if the patient is undergoing the latter form of CLAD, then you would expect to see it much like you see in ILD, where you couldn't see much change. And the second is, have you separated your cohort, which is large, a couple hundred folks, into these two forms, and does the oscillometry look different in the two forms, or as one might predict?
So the answer is yes, so and I think Annie Fu, who's the other graduate student working on this, just recently published a paper, and so the oscillometry is very different, and not surprisingly, the BOS folks have oscillometry that look like COPD. The RAS folks look like actually our IPF patients. The problem, well, I'm not going to say it's a problem, is that because, we began our studies in December of 2017. And so as time will progress, we will begin to see more and more CLAD cases. So between the time when this paper I just presented was, we had 26 patients with CLAD. At last follow-up, just before we came, I think that we were able to sort of retroactively identify that of that cohort, we have like 96 patients now. Of the 234 patients have now established CLAD. But I said part of the really, I think, treatment, finding a treat, there is no treatment for CLAD right now. And that's really sort of the holy grail in terms of lung transplant. But if you're having to wait 3 months, from the first time, that's a huge problem in terms, and then it's
the study design problems you pointed out are severe. And I think, as we all know, that if you don't, we know this in asthma, it's going to be true in ILD too, that if you don't intervene really fast and hard, you're not going to see much of an effect.
Julian.
Chung-Wei, that was an amazing presentation. Thank you. We're doing a study on children who have had hematologous stem cell transplants. So it's a little different than the lung transplant population. But one of the things that we're finding, and I'm wondering if you see this in your population, is that even though they may have normal resonant frequencies, and of course, they've had many treatments before their stem cell transplant, so we don't know if this is related to their treatments for their underlying cancer or treatments related or findings related to their transplant. But one of the things we're finding is that even though they may have a normal resonant frequency, at high frequencies, they seem to have a curve that doesn't obey the predicted increase in reactance that would be due to the inertive component. In other words, they tail off. So they have a normal resonant frequency, and then right past resonance, their whole reactance curve is depressed compared to what you would expect at high frequencies. And I'm wondering if you've seen a similar pattern. I mean, it suggests that elastic properties are taking over from the inertive properties, or at least competing with inertive properties at high frequencies. Have you noticed any patterns like that in your lung transplant population?
I think I'm going to have to answer this one sort of more indirectly, because what in our lung transplant population, the lungs tend to be a little bit oversized. So there have been a number of studies that have looked at size matching, donor recipient size matching, and the evidence is that the slightly larger lungs have a better outcome in terms of survival. And so what we tend to see post-transplant, even in all people with normal FEV1 and FEC, is that these are all mostly restrictive patterns. And so I think that, so we do see a shifting to the right in terms of the reactance curve. And we had a study that is now concluded actually in adult bone marrow transplant patients. And I will need to go back, Julian, and have a look at that data. We were frankly disappointed because when we actually started the study, what we were told, what we had anticipated was that, a quarter of these patients were going to end up with graft versus host pulmonary disease. And we did not see that. And I think that this is not really my area of, of clinical care, but I think that there has been a real change in terms of the protocol and the prophylaxis of the stem cell population, so that the graft versus host disease is not as common. And I don't know if Paul Robinson is still here on I saw him earlier online, but I know that he is in the process of collecting an international database of the stem cell transplant patients and the oscillometry values. And I don't know if he can actually weigh in on that. And I'm not sure that I see him here.
Yes, we've been working with Paul on this also. I mean, like you, Chung-Wei, you can ask anybody at CHOP. I'm kind of addicted to oscillometry. And one of the things I like about it is that like a flow volume curve, you can look at these resistance and reactance curves and, you know, get impressions from across the room, just like you can with a flow volume curve, of very clear patterns of abnormalities. So I think, you know, investigating those patterns becomes very interesting.
Thank you.
Thank you.
Okay. Last but not least, we have Joyce Wu. You can talk on the computer. I think it might be. First one. I don't think I'm sharing the screen. This one. Share screen. Where did it go? Am I correctly sharing it?
Yes, you are.
Okay.
Okay, thanks everyone for the invite. I know I'm standing between myself and the end of this seminar, so I'll try to make it short and sweet. We've done oscillometry since December 2017, as Sean White mentioned, so we've tested maybe over almost 2,000 participants at this time at our site already. So I just have 2 case studies to show or highlight today how oscillometry is important in addition to spirometry that we normally conduct. So at this time for the first case study, we're looking at a patient who received a single lung transplant. He was diagnosed with IPF and was confirmed with a pathology with the transplanted lung. At this time, I sort of want you to keep this CT image in mind as well as we walk through some of the oscillometry patterns and values. At this here, this is the first, or this is just the oscillometry values that, or the EFT and the oscillometry that we have done prior to the patient's transplant. At this time 0 here, this is at the marker or date that the patient received a single lung transplant. This transplant was considered uneventful. Patient was discharged at about 20 days post-transplant on room air. In about 8 days, the patient was brought in and had pair oscillometry and PFT done. We can see a slow or small improvement in the or actually no change in the FVC over time, and a marked increase in the AX values. 3 days later, patient was actually also brought in again for surveillance bronchoscopy. At that time, patient was diagnosed with grade 1 acute rejection. He was shortly admitted and received augmented immune suppression treatment. And about 7 days later, he was brought into the lab again and had PFTs done again paired with oscillometry. We see a significant improvement in the AX values in addition to the XY values as well. We did also see a small improvement in the FVC and the FEV1. Again, these are the 2 parameters that is used clinically around the transplant sites to see if there's improvement in patients and their progress treatment over time. However, in comparison, we did not actually see a significant improvement in the FVC and the FEV1 until about 3 months post-transplant, unlike the oscillometry values we saw previously. Just graphing it in a different point of view, we see that patient did achieve the best lung mechanics improvement in about day 40, again, just after the treatment of the acute rejection. And we can slowly see over time that even in about 1 year post-transplant here, the FEV1, or sorry, it's not here, but just the FVC value is still improving over time. So just to summarize in the oscillometry oscillogram, we can see that at the pre-transplant, the XY is marked increased, and just even in the presence of the acute rejection, we can see an improvement with the XY values. And again, shortly after the acute rejection treatment is significantly improved over time. And lastly, I think it was touched upon yesterday and even earlier today that the XEI, so the end inspiration reactants, this is at the post-transplant, we do see the slope that I think Jeff has brought up earlier. We see the marked difference between the end expiration and the end inspiration. Again, if negative 1.17, and again, we don't see this slope anymore immediately post-transplant, even in the presence of acute rejection. Again, there's not much, but slight improvement again after the treatment as well. So what does this tell us? So despite the existence of the native fibrotic lung, oscillometry still remains viable and capable of detecting rejection post-transplant. And we can see an improvement in lung mechanics demonstrated by the X5, XGI, and the AX. And it was previously assumed that the oscillometry is uninterpretable even with a single lung transplant. However, in this case study, we can see that oscillometry is indeed useful in addition to conventional pulmonary function tests. Our second case study is actually about this is a double lung transplant patient.
Can we ask some questions at this, at the first?
Yes. I
You
can
mind?
pause here. Yeah, no, I actually want to pick your brain.
Well, there's not a lot to pick. But
Because I'm actually a little not sure and stunned that this, again, I think we had a conversation last night that this monofrequency interbreath is quite considered normal.
I'm more intrigued by the disconnect between forced vital capacity and AX. I mean, my view of it is that AX measures basically the amount of lung that's being oscillated. And so why you would see a forced vital capacity changing and I'm sorry, AX changing and not FVC. I was wondering what was happening with TLC.
So the TLC is reduced. We do have the data or information. I just don't have it displayed or demonstrated here. I think there's probably about sort of two reasons why I think that's the reason why we don't see, we see a reduce in the FEV1 FVC. It's because, it's the conditioning of the chest muscles over time as the patient gets ill. And, there's a bit remodeling of the chest wall after the transplant over time. It's the patient continues pulmonary rehab and physiotherapy that, they will.
Well, that's why I was asking because, what a lot of people forget about is the fact that FEV1 is driven by the FVC, which is in turn driven by how large a breath you take in. Rube Cherniak taught me that years ago. I mean, you miss TLC by 100 cc's, 200 cc's, which doesn't seem like a lot. You'll get a significant change in FEV1 FVC. So the number one thing, and this as a therapist, you've got to take a really big breath and do it in a consistent way. So that's what caused me to wonder about that. The other one was, is there a lot of gurgling going on in these folks and wheezing and liquid in their lung? No. Okay. I'm just, again, curious.
I think along those lines, Charlie, is how much neuromuscular weakness? I mean, how sick are these patients pre-transplant? Does it affect their respiratory forces? And how long post-transplant does it take to recover your normal forces?
You want to do that one? I'm not
Joyce,
gonna
you
jump in.
No, unfortunately, we don't do MIPS and MEPS. And I think over time is that it's hard to say. I have seen like a single lung transplant patient that.
But as a therapist sitting there and talking, doing forced vital capacity, are they able to do it reproducibly?
Yeah,
Well,
I would say, a good 90% of these folks, like we're seeing them about 3 or 4 weeks post-transplant, they're able to reproduce these spirometry tests.
So they don't strike you as weak.
See, I trust that observation much more than You know, the fact
Yeah.
that you think they're doing.
But I mean, the other thing that I guess as our point of view working in the lab is that I don't exactly know how poor the condition was, physically, like
Yeah,
were
yeah.
they in ICU just before transplant versus someone that was, say, waiting at home for a
I mean,
transplant
the
that's still
exercise
attending
literature
rehab.
shows that you have to be, that the muscles have to be really fatigued before you start seeing drops in FEV1. So
So maybe just to put that into context, right, is that the patients, when they're put on the wait list for transplant, they actually have to come in to do the rehab 3 days a week
before,
every week. And so that's actually a requirement of transplantation. And for patients who are on ECMO, so the reason why ECMO had really completely changed the sort of pre-transplant sort of criteria was that by putting people on ECMO, we actually put them on the treadmill while on ECMO. And so they exercise during the time. So, and if folks are in bed rest for too long, that's when we really start having conversations about, delisting. And post-transplant, they also exercise, post-COVID, some of it is virtual, but it's supervised pulmonary rehab 3 days a week. But your question is actually a really good one, because we've been also looking at some of the longer, like some of the double lung transplant data, and it's very clear that the lung mechanics is improved, like the lung mechanics, the best lung mechanics as seen by the lowest, R factor 19, lowest AX occurs really early. So somewhere between within 46 to 57 days post-transplant. But if you look at the FEV1 to FVC and the TLC, because we do TLC,
We do
full
TLC
PFTs on all the folks, is that takes a long time to actually get to maximal value. And I don't, and if you look at those, I mean, this disconnect is very obviously there. And some of it is clearly chest wall remodeling, because, the little IPF patients have these tiny little chests. But that doesn't explain the COPDs. And I don't like that. This is where I think when Joyce and I were trying to figure out what cases to showcase, I mean, this is where I think, Jason, if you're still up there, Jason and Zoli, where the modeling would really help us in terms of trying to understand, because I don't really understand why we can detect changes on oscillometry with, if you looked in the CT scan, like that one fibrotic lung was significantly worse post-transplant than pre-transplant, because it's about a year apart.
I guess it just speaks to how all of the oscillometric signaling is going into the normal lung only. How much?
But those airways are normal on both sides.
Is that lung worse on the right, or really just because of relative hyperexpansion on the left side? That lung is more atelectatic rather than more fibrotic.
Yeah, I think it's a good point. The lung volume is certainly reduced on that lung post-transplant.
Yeah, no, that's certainly true. And we used to, like, a long time ago, we did some studies with, VQ scans post-transplant, but we haven't, and most of the perfusion is on the transplanted side, but the ventilation, that native lung is still being ventilated.
Sure. But it's funny that you also did a single lung myofusion as opposed to a pulmonary hypertension.
Well, thanks for the input, everybody. We're just going to move on to the case study number 2 quickly. Let me just scroll through. Again, this is a patient who received a double lung transplant, and we've been following this patient for about a little over 3.5 years. So we can see at about 3.5 years, the most recent visit, there's a significant decline in the FEV1. Again, as Changwei mentioned earlier, this is considered a 20% drop in the FEV1. And a poor patient normally would have to wait 3 months to come back in for oscillometry for PFT testing to diagnose whether they have CLAD or not. So our team was quick to acknowledge this decline. So we had plotted out all the different variables that we like to see if there was any significant decline or changes in the oscillometry parameters, as we're still learning to see what parameters may pick up changes. And we do see that there wasn't any changes. If you sort of stretch it out and look at it over time, patient did not have any change on the same day with the FEV1 decline of 20%. So as part of the normal routine, the transplant team was alert. Patient was brought in the next day for in-person clinic and was advised to repeat spirometry again. And surprisingly or unsurprisingly, the FEV1 is back up to the patient's baseline, which is usually about 2.6, 2.7 liters. And we can also see the oscillometry values are quite similar even to the 3 months prior at the 1,200 days. So we talked to the patient and say, why do you think there was such a decline on the day previously? So the patient said it might be due to the language barrier. He does not speak English natively. So what does this sort of suggest in terms of oscillometry? We think that, despite conducting, the patient having conducting spirometry on multiple occasions now, probably looking at 5+ years, post and pre-transplant, language barrier can still attribute to poor performance. And it suggests that, even with a language barrier, patient can still conduct an oscillometry test according to the guidelines, even with minimal coaching. And it allows us to understand the mechanics of the lungs with the minimal effort from patient.
If you hadn't had the oscillometry to say, let's do the spirometry again, would have that patient gone on to biopsy at that point?
Yeah.
Yes.
The oscillometry saved a biopsy.
Yes.
Yep. Absolutely.
That's an important point.
See, what I would have done at that point is hold the records and look at the flow volume loops.
I looked at the flow volume loop. It basically is just like a reduced flow volume loop of the previous day. So if you look at
Well, that actually can't be correct, Joyce, because if that were the case, then the forced vital capacity would go down, which it didn't. You show it there.
Yeah. So I don't really know why. It just
that doesn't make a lot of sense to me. I like to look at the loops themselves and making sure that maybe the wrong.
I didn't test the patient. I can only say that.
But
I didn't test the patient on that day.
Well, you know what? Next time out
there's the problem.
That's the problem. That's right. You got to blame somebody else. And but I didn't. I
would have got that. Joyce wasn't there.
I wasn't there.
Joyce,
so I want to thank the Pulmonary Functional Lab at Toronto General and anybody at the Child Lab for contributing this to the study. And unfortunately, due to Chung Wai's addiction, we're still continuing with this awesome llama tree.
Well, before I do the final wrap up, I just want to make a point about time management versus profession. At this time yesterday, when a doctor was in charge, we were maybe half an hour, and we would get blamed as having always being late for time management. But this morning, an engineer was in charge, and we are an hour and 15 minutes late. It's an N of 2 experiment. I'll let you draw your own conclusions. But seriously, this has been awesome. And I am really looking forward to the projects that may come out of the networking supper last night. I'm looking forward to further work on the projects presented today and yesterday. And I really am looking forward to hosting you all back here in Montreal for the 8th annual event, which will be the same time frame the last Thursday, the last Friday of July. And I think our new venue, we all agree, it's a keeper. And we'll probably come back to this same room and do a supper at Thompson House like we did last night. So for those of you out there, please book your tickets now, tune up your cars, and buy your bus tickets. I don't care how you get here, but I really want to see you guys in person, because as much as this works seamlessly over the internet, you guys missed a wonderful time last night. So thank you, everybody, and I'll see you next year. And with this, I'm going to close down the seminar. Bye.
I think we all owe Ron a big thank you for being the stalwart, really pushing through these things for the 7th, 8th times, and all really grateful to the company pulling this. Well, thank you so much.
Well, it's a lot of fun. It's a great pleasure, as well as an honor. So I guess it's a win-win situation here. Thanks.
Thank you.
Okay, bye-bye, everybody.